Hi guys, welcome to my channel. Let us discuss some chemistry topics that are relevant to your next exams, be it the trial exams and also the final exams. And beyond, of course, for those who may wish to upgrade next year, this may still hold relevant. I must say that I am really grateful, guys, to all of you who continue to support my channel and to see the subscriptions, the sharing of the channel. I see all of these in the analytics. It's quite impressive, guys, for such a small channel to truly, be maintained by all of you. It's a great honor for me. I'm truly and deeply humbled by all of that. I just hope you guys never get tired of it and you continue to do so that we can contribute some good into our society and perhaps make our country a better place. In fact, even better than it already is. We can all agree that our country is truly a good place to be in and for all individuals, and it is a fertile ground for any form of vision, dreams, and some success. Okay, so we should not lose that over the noise that is made by those who are just, opportunists and many other kinds of people of different forms and different types, with just different motives, which we should not align ourselves with, but rather a common cause, a greater good. So I am really thankful, guys, and please continue to show your support. I will do my best also to give you the best that I can, despite my very busy schedules, which unfortunately impacts on the inconsistency of my posts. But I will do my best to ensure that at reasonable time intervals, there is some information, given in your direction. Now, there's these three that I like to call the dangerous trio. This is, rates of reaction, chemical equilibrium, as well as acids and bases. Most often these three topics tend to pose a challenge to students, and because of fear and this general impression that these topics are difficult, students tend to drop marks when they get to these topics. But I will try to show you guys that there isn't anything here. Yes, precision is key, and that's where most of the students lack. It's precision. So key in these three topics is precision, because if that is in order, everything falls into place. Alright guys, this document was prepared in the Free State in 2023. Okay, so we're going to use it to kind of revise, and of course if you want a copy, it's going to be available in the description section of this video. Please go have a look there and find yourself a copy. I will put it there. By the time this video is available, all of these documents will be there, including this memorandum that we're going to produce for some selected questions within this document. And please do your part, guys. Practice the rest of the examples. In fact, exhaust all these questions, because this question bank is using past exam questions, and for each section there's tons of questions relating to that topic. So it gives enough practice to say, okay, you're comfortable with the topic. As you move on, you will get some notes for each, and then of course some number of questions from past exam papers. This is very helpful to then structure how one should study for these exams. Alright guys, let's get into business. Now, we're talking about reaction rates and energy in chemical reactions. Okay, so when we talk about energy, it has a particular impact on what we call the heat of the reaction, the delta H. Now, how do we obtain this? As you may recall from grade 11, delta H is energy of product minus the energy of reactants. All right? So that's how it is done, and no other way. Okay, please remember this. As I said, guys, precision is key in these topics, so we need to know the detail. Unfortunately, if the detail is not known, the whole thing becomes a disaster. All right, so that's basically how we obtain this. We just need to remember that. Otherwise, when we talk about the heat, this can give us an indication whether the reaction absorbs energy or releases energy during a chemical reaction. Now, this brings us to exothermic reactions as well as endothermic reactions. Now, what do we know about exothermic reactions? These are the reactions that release energy, whereas endothermic reactions absorb energy. Now, in essence, these exothermic reactions essentially are what we would call spontaneous reactions. They are largely spontaneous reactions, okay? Meaning they just take place on their own, or perhaps we can easily say they self-maintain, because others, they just need to be started and then they self-maintain. In essence, these are exothermic reactions, despite the fact that they don't occur automatically, but once started, they continue on their own. So these are still classified under the spontaneous types. Now, of course, we may think of some examples and say perhaps ionic exchange reactions are simply spontaneous reactions. Again, some may need to be studied and then they continue, others occur automatically. Right, so we can talk of acid-base reactions, and we know that once we pour an acid and a base into a container, the reaction takes place. So these are spontaneous reactions. And we can see that some redox reactions, especially for voltaic cells. So the voltaic cells or galvanic cells involves spontaneous redox reactions. All right, we can also add this category, the combustion reactions. Of course, this is when we're dealing with, the combustion of hydrocarbons. These ones, they just need to be started. And once started, they self-maintain, although they don't just occur automatically, but once started, they self-maintain. So it helps to keep this in mind, folks, that, okay, when we talk about exothermic, largely these are spontaneous reactions, and the types that we can identify as ion exchange reactions, acid-base reactions, where these two are somewhat relatives of each other, even including redox reactions, because there's some ionic exchange reactions that take place there as well. So, yes, combustion reactions. But as we can see here, they release large amounts of energy. And this energy we can use for many different purposes, like firewood. We want to produce heat to warm ourselves in winter, or even to cook, or to generate electricity, or whatever we need to do with that heat. Of course, redox reactions in voltaic cells is what creates our cells that we use for our remote controllers at home and things like that. Acid-base reactions have wide, applications as well. So these are very important to keep into perspective. And of course, if we just analyze this energy graph for an exothermic reaction, we will see that the energy of the reactants is greater than the energy of the products. This already shows that we release a lot of energy when we form this product. And as a result, since we know the formula to determine our delta H comes up negative, because the energy of the products is smaller. And now when we take the difference from a smaller number and we're taking out a bigger number, we end up with a negative answer. So as a result, delta H is less than 0. So that's the essence of this. Please guys be able to draw this and be able to understand. Of note, we will see that the activation energy. So our activation energy, we can see that it's quite a small amount of energy. And what is this activation energy? It is the energy of the activated complex minus the energy of the reactants. This is very important to also realize. So that's essentially what we can learn from this energy graph for an exothermic reaction. Now when we look at the endothermic reaction, which is the one that absorbs energy, we can see that this is under the class of non-spontaneous reactions. Okay, so these reactions, if we can take some examples, we can talk about the redox reactions. This is for the electrolytic cell, electrolytic cells, right? And we can talk about some decomposition reactions of substances or compounds. So normally these don't decompose spontaneously, although some can, but most compounds do not. So a bit of energy is needed to maintain the reaction, because as soon as that energy is taken out, the reaction literally stops. Okay, of course guys, you can think of other examples here, but I just have these two in mind because in the curriculum for matriculants, this is the common ones. Right, so if we look at the energy graph here, we'll appreciate that the energy of the reactants is smaller than the energy of the product. As a result, the difference is greater than 0. And of note is that the activation energy is much larger than in the exothermic reaction type, okay? Because we can see that this one is maintained by a continuous injection of energy. It does not self-maintain. All right, we need to drive this reaction from start to finish. All right. Excuse me. So that is essentially, guys, what needs to be understood about these types of reactions. Then, of course, activation energy. One may need to be able to define what is activation energy. Right? Right. So this is the minimum energy needed for the reaction to take place. And of course, on an energy graph, it is equal to the energy of the activated complex. We can just say AC minus the energy of reactants, R. Okay. So please remember this as well, because it can come in handy in answering questions relating to that. Of course, there may also be a bit of a question on what is the activated complex, right? Key to this is that this is the unstable transitional state of our reactants as they change into products, all right? Again, guys, please read and read with understanding. This is a good summary for those who study, but of course, guys, don't exchange these summaries for studying in the textbook. Please study the textbook and try to understand. Then this becomes a very good summary at the end. Okay, so we may look at the effects of a catalyst on these energy curves, of course, depending on which type we're looking at. Either one, it doesn't matter. What matters is that a catalyst will essentially lower the activation energy for any reaction, be it exothermic or endothermic. It becomes lower than it would originally be. And again, we need to be able to draw this graph. Sometimes it gets asked in the exams that one should draw a graph when there is an involvement of a positive catalyst, for example. But I wonder what would happen when someone asks a question on a negative catalyst. What would happen? Obviously, that one should raise the activation energy. So because these examiners have become so tricky, please guys, be on the lookout. Certain things may just come for the first time. Because if this is within the logical framework of a student doing matric, it can be brought in, even if it's not anywhere in the documents that you guys have. The fact that you can reach it should be a positive thinking for a student. So please, as much as we often talk about positive catalysts, please do consider negative ones as well. And imagine what these graphs would look like if we were to have a negative catalyst. Obviously, a negative catalyst would do us something like this. We would have something like that, perhaps. Maybe I'm doing it wrong. It would have to latch onto this for sure, but raise the activation energy needed, I suppose. This is just a thought. I don't know. It may come, may not come. You never know. So what does a catalyst do? It increases the reaction rate without undergoing a permanent change. So there is no permanent change, but it just facilitates that reaction. Okay, it's like a teacher. When the teacher is present in class, students tend to work within reasonable time. But if a teacher was just to leave students with work and never come back, these guys would never finish what they're doing. So this is just the job of a catalyst, is just to police that reaction so that everything goes on well. But the teacher does not necessarily write the exam themselves, right? It's always the case. Right, folks, we need to also know how to define the reaction rate. So this is the change in the amount. I would prefer that in the amount rather than to specify. But again, it's okay to specify, if you will. It is accepted. But the amount captures concentration, number of moles, mass, or volume in the case of gases. So it's very important to try to give a rather broad definition than a specific definition. But at the same time, there's no harm. It is widely accepted that you can use any of those. That would represent the amounts. Right, so this is the change in the concentration, or should we say the amount of reactants or products per unit time. K is also per unit time. So it's a change of the amount per unit time. So this is very important. Very short definition and easy 3 marks. In my opinion, definitions as short as this should essentially just get 1 mark, because that's just giving too much for less. But again, we don't set the standards. We follow them instead. Right. So again, guys, let's note the factors that affect a reaction rate. So the nature of our reactants, or we can say sometimes the state of division. Right. We know that solids versus aqueous solutions versus gases and stuff, that can affect the reaction as well. Okay, we can talk about concentration. As we know, higher concentrations translate to a faster reaction rate. Why? Because there's more particles when the concentration is high per unit volume, and so there will be more regular collisions of the molecules, and some of them have enough energy to cross over into products. The surface area, of course, the surface area we're talking about mainly solid versus powder. For solid substances, I should say. So versus granules, maybe solid versus granules or ribbons, or chips versus powder, but I'm just going to simplify it into those two, but we know there's more in there. Again, we would know that a powder would have a larger surface area than a solid. When I say solid, perhaps a rod, because all of these are solid. Maybe let's put it differently, because I'm almost confusing myself too. So we can say this is usually in regards to solids. When we talk about powder, we can talk about granules. We may talk about chips, and we may talk about a ribbon, and perhaps a rod, things like that. So this pertains to solids in a way, and we know that powder is superior in surface area, followed by granules, and then chips or ribbons, and then the rod. Okay, so temperature, again, we know that the higher the temperature, the faster the reaction rate will be. Now, the influences of a catalyst, very important. We need to know that a catalyst increases the reaction rate without undergoing a permanent change, right, itself. So it's just a facilitator. Now, we need to know how to calculate the reaction rate. But now what I would highlight is that when we are using reactants to calculate the rate of a reaction, we need to remember to put a negative in front of that ratio, because we would end up with a negative answer. So this is to protect a student to present a positive answer. But remember, the method sometimes does not matter. What matters is the answer quality. So a student who can just perform the normal calculation and the answer comes out negative, but presents the final answer as positive by perhaps neglecting that negative answer, that would also be okay. But then to then protect those who may not realize that we don't accept a negative answer in physics or in chemistry, so there has to be a final answer that is not negative, however one gets to that. Okay, but this is just the necessary precaution. Now, important again is the unit of measurement. So with reaction rates, we don't really put too much emphasis on what is the SI unit. We don't really put one. Any that is provided in a particular question or scenario would be the one that we adhere to, or we follow the instruction. However, we are given, the examiners hold the discretion to just ask from the student to present the answer with a particular unit of interest. Of course, examples are mole per decimeter cubed per second, could be grams per second, could be decimeter cubed per second, or mole per second, or even can be kilograms per minute. You never know. So here we don't really waste time, but we need to be able to realize that there's a bit of flexibility in how we can present the answer. Most important is to adhere to the instruction given, right? Now, we may have to look at some practical stuff where we talk about independent variables. Of course, this is the variable that is changed in the experiment or between experiments. And of course, there are examples provided here. And when we talk of the dependent variable, it's usually the reaction rate, since in this topic we are dealing with that. So this is usually the reaction rate. That is usually the dependent variable in questions of this nature. But be careful, there may be a lot. Of course, we may talk of controlled variables. These are the ones that we are to keep constant so that they do not influence the result in any way. All right, so that's the essence of that. Of course, guys, it often gets asked for a student to formulate an investigative question. So we need to be able to ask an open-ended question rather than a closed-ended question. The question must not be answered with a yes or a no. That is not acceptable, okay? Hypothesis, well, we don't really get to this topic, or at least to this extent in our experiments. But again, you never know. A question may be asked that formulate a hypothesis about, a certain relationship between two variables, which later we can then prove, is this hypothesis true or false? You never know. Examiners have become very skilled. So these are things to think about. And then, of course, we often get asked to make conclusions, all right? So when given a summarized form of data, we may have to make conclusions by looking at the trends or do some form of an analysis that may eventually give us an answer. Okay, guys, so this is very important, okay? Right. So again, the practical skills here come in handy. You read through all of these on how to measure products and what do you see on the curves and what do they represent, things like that. Because we know that when the curve flattens, this is when the reaction has stopped, okay? But on the rising or decreasing segments, this is when the reaction is ongoing. And of course, looking at the gradients, the steeper the gradients, the faster is the reaction rate. The more gentle the gradients, again, we're talking about the reaction rate decreasing. So this is very important to be able to look at, especially for practical purposes. All right. Now, of note is the collision theory. We need to understand and to be able to use the collision theory to explain differences in certain reaction rates. Of course, this is when we are comparing perhaps two experiments as to why the other one is expected to be faster or why is the other one faster, things like that. Okay, very important. And the emphasis here is on collisions, okay? Collisions. All right, so we don't talk about elastic collisions because elastic collisions are ineffective collisions. So you see, we can think of it momentum-wise. So here we don't want to hear about we don't want to hear about elastic collisions because this means those are ineffective collisions because there would be no chemical change. But the favorite collisions that we want in a reaction are inelastic collisions. All right, so that is what is very important, guys. And we know that in the theory, we may see what I call elastic collisions, where there's collisions, but they don't have enough energy to then transform the particles into products. Right, so for collisions to be successful, or we call it effective collisions, what must they be like, or what are the requirements for this? Right, we know that the reacting particles must collide with sufficient kinetic energy, meaning one that is greater than the activation energy. And we need also a correct orientation of the colliding particles. Of course, this would go to geometry of substances, knowing what are the areas, exposing those, empty orbitals that can then share electrons if we're having a covalent bond, or whatever, electron transfer if we're dealing with an ionic bond, you name those. Right. So of course, guys, this is just me stretching this. Otherwise, it's not as complex as I'm making it to be. Then again, we need to be able to deal with issues of the Maxwell-Boltzmann distribution curves or energy distribution curve. All right. Again, here, what is very important is to know factors that can affect this and how this can be affected. Key to all of this, folks, is to know that the area under the curve represents the total number of particles present, okay, in a particular reaction, or should we say, let's put it that way. All right, so this is essentially what is going on, guys. And of course, we will see that we often have the activation energy, included there. So we should remember that it is indicated on this curve. Right. Again, guys, read through this and understand what's going on. So again, folks, we need to also think about, the effect of temperature, whether an increase or a decrease, on how this Maxwell-Boltzmann distribution curve would look like. As we can see in this case, we see that T2 being greater than T1, we start to see the curve essentially shifted to the right to some extent, and of course it's to the right and down because the peak is much less than it was initially. And of course, when the temperature decreases, it shifts back to such a position. So this is a to and fro type of a thing. So we need to know this. Again, the effect of a catalyst, that the activation energy is shifted a bit back. That means we're lowering it so that more particles have sufficient kinetic energy. Okay, then we can have more products much faster than we would without a catalyst. So these are very important things to think about. Of course, guys, what happens when we increase the concentration or the amount of the reacting particles? We'll start to see that we obtain curve A, right? So nothing changes. The average kinetic energy is the same. If we were to draw it, it remains the same. Okay. Otherwise, there's just more particles, meaning there's more area under the curve for a given region. Okay. Right. So that's about it, guys. Again, folks, there's nothing that beats knowing definitions and, of course, terms in a particular chapter. It is unforgivable to go without knowing these things, because you may be asked a silly question as to what is a mole, or define a mole, right? So it's very important. So it's very important. As you can see, that definition is quite technical, but a lot of people may not know how to define this well. But again, there are many ways to define things, but rather be as precise as possible, as I said. So this one says 1 mole of a substance is the amount of substance having the same number of particles as there are atoms in 12 grams of carbon 12, okay? Or the carbon with mass 12, I guess. Right. So these definitions, if not well presented, may somewhat cause pain for students who do not care to pay attention to detail. Again, we sometimes may forget what STP is. That is standard temperature and pressure. So we need to remember these, because these were taught in grade 10 perhaps, and now students tend to forget. Of course, this is to suggest that 1 mole of any gas occupies 22.4 decimeter cubed, okay, at 0 degrees Celsius. That is at 273 kelvins and at an atmospheric pressure, or 1.3 kilopascals. Very important. Again, you may be asked a silly question like, what is a molar mass of a substance? Very simple and basic, issues may be very, very difficult to handle if not taken with care. Again, guys, we may have issues of this nature that we need to think about. When we talk about a percentage yield, percentage purity, and percentage composition, we need to know how to handle questions on this in this regard. And these are usually the popular questions in these topics, with rates of reaction, chemical equilibrium, and acids and bases. So those very big signature questions, they tend to require issues of this nature, so we need to know this. Again, the issue of limiting reagents, it's very, very, very important when it comes to these topics, because it gives us an indication of when the reaction would stop and exactly how much would we expect of a product. Which one is responsible for how much of the product we are going to get? It's the limiting reagent. And again, this can be asked in the form of a definition. So we need to remember these. Right, we've spoken about the others already. And of course, guys, we cannot overly emphasize the importance of all details here. So precision, 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 guys. So this is why you need to work on these topics without putting too much pressure on yourself, so that you understand them. The moment you do, it becomes easier to speed up in answering questions, because these questions are not really difficult to answer, but they can become challenging for those who are not as precise as possible. So let's take this question 1. This came from November 2014, and we're just going to answer this to just show how a student is expected to respond to questions in rates of reaction, and of course all that is associated with these questions. So let's deal with this question 1. Now we just hit with the definition, reaction rate in words. Okay, so you just go straight into it. We can say it is a change. It is a change in the amount of a substance. In fact, let's not say a substance, in the amount of reactants or products per unit time. Okay, so what is important is to say that this is a change in the amount of either reactants or products per unit time. So these are very important issues to capture. So however one phrases this, what is important is to make sure that it's either we're describing a rate of change or we say it's a change per unit time. There are many ways to put these definitions, guys, but whatever you choose, make sure you can present well. Right, so let's look at the next piece. We are told that learners use the reaction between impure powdered calcium carbonate. Can you see this is impure calcium carbonate and excess hydrochloric acid. Once the reaction partner is essentially in excess, this means this calcium carbonate becomes the limiting reagent. I don't know why my writing this always dies down. Why can't I relax? Limiting reagent. Right. Okay. Good. Because when I relax, I write better. But I don't know. I always have this increased, we call it psychomotor activity. I just have no patience, I guess. Right. What we were doing this for, to investigate reaction rate. So we know that this is our dependent variable. So we can see a balanced chemical reaction for this. Again, if we look at this reaction, what will we see? We've got an acid with calcium carbonate, we're producing salt, water, and carbon dioxide. And of course, what is this reaction? It's an acid-base reaction, right? And of course, if this is an acid-base reaction, what do we know? It's spontaneous. And if it is spontaneous, we know that this is an exothermic reaction where delta H for the forward reaction is less than 0. So this reaction liberates heat. And of course, you will recall, those of you who do practicals at the school laboratory, whenever you touch or hold the test tube where this reaction is taking place, it actually becomes much warmer than it was at the beginning, to prove that this liberates heat. And you will see that the reaction pretty much continues without being given extra energy or even energy at all. As soon as we mix these two in the test tube, the reaction takes place spontaneously. All right, it helps again, guys, to think about these things because they can become an issue. We need to know when we are given a reaction, we need to know exactly the type, so that when questions relating to that type of a reaction come in the questions, we are ready to respond to that. Because the fact that we're doing reaction rates, it doesn't mean other related issues are not going to be asked, okay? They may be asked, and sometimes we get surprised because we often expect only questions on reaction rates. No, this is chemistry, guys. We can ask anything, anywhere, okay? You may find yourself being asked, what is the delta H of a redox reaction in the electrochemical cells? Any one of them. You may be asked, what would be the delta H? And you'd be like, but this is not reaction rates. Who said when you are in that section, you're not supposed to respond to that? Because you're still doing chemistry. So please, folks, stop caging topics to a particular segment of the question paper. That's not how it works. We compartmentalize these for conceptual teaching, I guess, so that you understand the concepts without mixing them. But the end goal is to have a student who can be able to integrate those topics. Right, let's go on. So they perform 4 experiments under different conditions of concentration, mass, temperature, as shown in the table below. They use identical apparatus in the 4 experiments and measure the volume of gas. Can you see we measure the volume of gas released in each experiment? So this is an indication of the product. This is the measurable type of the product, okay? Because the others may not be so easy to measure. Okay, so we can see that experiment 1, okay, we used a 1 mole per decimeter cubed concentration of HCl, 15 grams of calcium carbonate, that is impure, and then 30 degrees Celsius of temperature. All right, okay. So we're basically trying to speed this reaction up because it can pretty much take place at room temperature. And mind you, room temperature in chemistry is 25 degrees Celsius, okay? It's not the general 21, right? Of course, experiment 2, what we see, the concentration has been halved, but same mass, same temperature conditions. So between 1 and 2, we can see that what we would call the independent variable would be the concentration of HCl, because that's what is different between those two. Otherwise, everything else looks the same. And we look at 3, we've got, again, 1 mole per decimeter cubed of HCl and then 15 grams of impure, but now the issue has been the temperature. So between 1 and 3, the independent variable becomes temperature here. Okay, and then we look at 4, again we see that same concentration as in 1, but we have added more of the impure calcium carbonate, so we've increased the limiting reagent, and this means we're going to produce more gas than we would produce in the other experiment. And of course the temperature is 40, so there's 2 things. So between 1 and 4, we cannot really say it would be a fair comparison, because you see there's 2 things that are changing for experiment 4 compared to 1, so that would not provide a very nice comparison. But we can safely compare 3 and 4 because there's only one difference. The difference is the amount of our limiting reagent. So again, guys, think about this thing. Sometimes you get asked a question of whether is that a fair comparison versus not. So remember, for a fair comparison, the two should differ by only one variable, not more than one. If that's the case, then it becomes an issue of whether is it reasonable or not reasonable. Again, this can be quite confusing. So, but yeah, that's the idea of all of this. So guys, it helps to study the table and understand what it presents. Right, let's get to 1.2 now. It says the results of experiment 1 and 3 are compared. So is this a fair comparison? The answer is yes. Why? Because we've got the same concentration of HCl, we've got the same mass of the limiting reagent, but the only difference is the temperature. So they differ by just one variable. So that's a fair comparison. So we can safely compare these. Now we need to write down the independent variable. Okay, so this is the one that's changed. So what is changed between 1 and 3 is the temperature. So that's what we're going to write, 1.2.1. It is the temperature. So can you see, guys, studying the definitions is very important. As you can see, precision is key here. These are not difficult questions, but precision is key. What is the dependent variable? Of course, it's the reaction rate. That's what we are trying to look at. Now, we then have to use the collision theory to explain why the rate of reaction 4 will be higher than that of 3. Again, is that a fair comparison? Yes, because everything else is the same except for the mass of the limiting reagent. So we can safely compare there. So of course, now we need to structure our argument by stating what is what. Okay, so we need to state the difference between these two and the effect of that difference, and essentially we then conclude what would happen here. Right, so let's go for it. This is a popular question and students need to learn how to answer it nicely. So we can say, well, in experiment 4, the mass of the impure calcium carbonate is greater than that of experiment 3. Okay, in fact, you can just choose one experiment and discuss it in comparison to the other. We can say the mass of calcium carbonate is greater than in 3. That is the difference. We state the difference. So what will this difference make? We know that there will be more molecules than in 3. There will be more molecules than in 3. Now, more molecules means there will be more regular and effective collisions per unit time will occur than in 3. Therefore, the reaction rate will be higher than in 3. Okay, so very important. So essentially we state what is different between the two and what is the effect of that. So if it has a greater mass of calcium carbonate, we know that there will be more molecules per unit volume. In fact, let's put it that way. More molecules per unit volume. Okay, and that means more regular and effective collisions per unit time will occur than they will in experiment 3. Therefore, the reaction rate will be higher than in experiment 3. Okay, so this is very important, guys, to structure the argument like that. State what is different between the two, what is the effect of that difference, and how does the collision theory come in, and what would be the end result in terms of the dependent variable. Okay, so let's do it. So essentially, guys, I mean, there's lots of things to say, but again, that is key for me. This is very key. So the conclusion here matters more. The difference is pretty obvious, but the essence of that difference is what matters when we can put sense into it. Again, this could be easily 4 marks when we also capture the difference itself. But we'll just stick to the marks allocated and try to, use that. All right, so the next one says, learners obtain graphs A, B, C, and D below from their results. So that means they plotted what they got here in terms of the volume of carbon dioxide over time. Right, we can see that for each graph, we see that graph A had an explosive amount at the beginning, and then it evened out pretty quickly, and then it stayed the same. But what we see is that the height of that graph is greater than the height of this B and C, which is the same, by the way. And then also we see that D has pretty much the same height as well as the others. All right, okay. Why do we know this? It's all because they each have the same mass of the limiting reagent. So we expect them to bring us the same amount of carbon dioxide. Okay, this one is expected to be bigger because we can see that the limiting reagent had been increased, and we know that the volume of the HCl was in excess, meaning it remained bigger and out of proportion to that of the calcium carbonate. So if we increase the limiting reagent's mass, we are effectively increasing the amount of the product. Right. Okay, so the gradients here, guys, represent how fast these reactions occur. As we can see, reaction D is less than that of C, which is also less than that of B, which is all three less than reaction A. So obviously, if we look at these graphs, we would see that A should represent experiment 4, and B should represent experiment 3, and C should be experiment 1, and D should be experiment 2. It helps to look at these graphs, guys, with an understanding of what is going on. Okay, that is key. That is key. Right, so question says, which one of the graphs A, B, C, or D represents experiment 1? And fully explain. Do you see that? Nice, 6 marks. Fully explain. So this is not a very simple thing. Of course, which one represents experiment 1? We saw that it's going to be graph C. So it is C. So now we need to fully explain. Now, as we see there's like 6 marks there. So there is a lot for us to say. Now that means we need to compare the rate of that reaction for experiment 1 to all the others. That's just the idea right there. So this is a very nice and tasty issue here. Okay, what are we going to say, guys? We will say the gradients. We'll start by the gradients because for me, we can almost tell that the rates of reactions are different, but we learn this from the gradients. And from the gradients, we'll take it to the exact parameters on the table. So I'll just say the gradients for C are less steeper than those of A and B, while steeper than that of D. Okay, that's our first point. We're comparing the gradients. What does this mean? This implies that the reaction rate rate of C is less than those of of A and B, while being greater than D. Right, now we need to get to the gist of the matter. Why is it so? Well, we know that essentially experiments 1 to 3 have pretty much similar conditions except for temperature and concentration of the HCl. So at this point, I think it would be wise to choose the difference between experiments 1 and 2, and then 1 and 3, and then 1 and 4. Okay, because at this stage we will not be able to just bunch all of them. First, we established that the reaction rates were different, but now the question is why? I think that is the part that says fully explain. We can say, well, C and D we can say C, which is experiment 1, differs with D, which is experiment 2, in the concentration of HCl used, leading to less molecules available for effective collisions. Okay, differs with D in the concentration of HCl used, leading to less molecules available for effective collisions to take place. In D than in A. In C. Of course, D is experiment 2 and C is 1. Okay, hence the reaction rate of C is, in fact, guys, at times I get tired, is greater than that of D. Okay, so What am I saying here? C differs with D in the concentration of HCl used, leading to less molecules available for effective collisions to take place in D than in C. Hence, the reaction rate of C is greater than D, or we can say the reaction rate of D is less than C. Then we go on and take a jab at 1 and 3. We can say C, which is 1, differs with basically B. Okay, B is experiment 3. All right, so I hope I'm not confusing myself. This one differs with okay, what am I saying now? C differs with B in temperature. Okay, they differ with the temperature, right? Now what do we know is going to happen? We can say such that the average kinetic energy such that the average kinetic energy of molecules of B is greater than C, leading to more effective collisions. Hence, B has a higher reaction rate than C. Right, so again guys, this is just killing it slowly, and of course using our collision theory to kind of, bring ourselves into speed. I know my writing is horrible guys, but hey, there's nothing I can do about it at this stage. If I was to try and write nicely, I would never finish, seeing that I talk too much. All right. And then the last bullet, sorry, we can say again C, 1 differs with, now this is A, which is experiment 4, with, now this is going to be quite difficult because we cannot compare 1 with, we can't compare 1 with 4 easily, okay? We cannot. But again, perhaps we can, but what I would prefer though is to compare 3 and 4, but we already have, okay? We already have, so we can say with C being greater than, having the reaction rate greater than 4, it is already greater than that of B. We don't need to go into this one because we've already done it. So we can say since A, which is the reaction 4, has a higher reaction rate than experiment B, which is 3, as shown in 1.2.2 above. It therefore is clear that it is clear that A has a greater reaction rate than C, which is experiment 1. Okay, so there's no need to really get into the detail here. I don't want to waste time explaining that, there's going to be more of the products, but again, we could still say it and say that there's less number of moles in terms of, molecules themselves and the average kinetic energy. So there's two things there. So in essence, we don't really want to get into that. We don't want to get into that. But again, I could be dropping a point for this. I could be dropping a point. Maybe let's not do this way. It's dangerous. It's dangerous. We already got marks for this, so we should not try to be silly. Perhaps we can say C1 differs with A, which is experiment 4, in the mass of calcium carbonate and temperature, which means that there will be more molecules or particles, molecules with a higher average kinetic energy. Kinetic energy, should I say average or sufficient? Okay. Okay, so again, it doesn't really matter, I guess. There will be more molecules with a higher average kinetic energy and sufficient kinetic energy to form, or should we say to, energy for effective oh God, I hate to have to write an explanation for effective collisions, right? You can say hence A, which is experiment 4, will have a higher, will have a higher higher reaction rate. Okay, of course guys, I tried. I hope you can follow. Of course, for 6 marks here guys, we have to really do the justice, otherwise we're not gonna get the marks. So there's no easy way. Sometimes it's just the hard way. As long as we put our arguments in a coherent and very sensible manner, we should be fine. So Of course, folks, I would say comparing the gradients and saying exactly what these gradients mean, I think this is key, because that's the evidence that the reaction rates are greater. And then, of course, essentially these three, usually I would say 2 marks for each argument, 2 marks for each argument. And perhaps we can, this should have been maybe 7 marks, because again, we needed to first establish what is happening. But again, we would not necessarily mark this. Why? Because we already spoke about the reaction rates being greater already within the arguments. But perhaps that opening statement would be essentially, what could I say, it's an introduction to all of these arguments, that at least the evidence on the graph is that those reaction rates are not the same. At the same time, not being the same, what seems to be the issue? Then this is when we get deeper into the 3 categories. So I suppose that is essentially where those marks sit. Of course, guys, as I said, there is a formal memo to these questions right at the end of this document, so you will be able to go and have a look as to how this is phrased. I don't really waste my time to go and check there, because I end up not showing you guys how to survive an exam properly, because remember, you won't have the memo in your hand and you won't see it. You will see it when it's all said and done. So what do you do to ensure that you get marks anyway? So that is the essence of this video. It's not about being memorandum correct. It's all about being scientifically reasonable. Right. Anyway, let's go to 1.5, which is usually where a lot of students choke, because now this involves a stoichiometric calculation. Now, what I like about this document, the people who prepared it, they always provide a numerical answer right next to the question. It's like those old textbooks, which are probably underlooked, or should I say overlooked, because those books did not show you how to solve the problem, but they showed you the answer so that you know when you're wrong, and you just have to find the right way. And that made us to be very strong, because we always had to trust the process. We always had to be precise. We always had to know exactly what we're doing. At the end of the day, we never struggled to meet new questions, because nobody ever showed us how it's done. You just see what to do with all that you have and all that you've been taught. So sometimes that way of doing things is quite attractive. I would rather, even these memos tend to present the answer only. Okay, that would be unfair, but I suppose it should, so that students can actually stop being lazy, because having these memorandums available has created much weaker students than it used to be the case before, because students trusted their ability and they had to learn how to get things done, rather than, Devin must stop, guys. They just want to sell me things anyway. I hardly use this number for anything, so if I get calls on this phone, I know it's just commercial bullshit. Sorry for the language right there. Those people just like to waste our time and money, and yet they really don't keep the end of the deal the way that you essentially expect. So it's just ridiculous. I think at this stage, this commercial issue is just becoming a cancer right now. Anyway, that's me just being me, so I'm probably overreacting. Right, okay, let's assume, oh, by the way, let's read. When the reaction of experiment 4, okay, reaches completion, the volume of gas formed is 4.5 decimeter cubed. Assume that the molar gas volume at 40 degrees is 25.7 decimeter cubed. Now the question is why? Because we said the molar gas volume at STP is 22,4 decimeter cubed. Right? Now why is it now 25? Why does it increase? Why? You ask yourself that question. But remember, we are talking about a real gas here. Carbon dioxide is a real gas. And we can also talk about what we call ideal gases. Real gases versus ideal gases. So again, guys, you need to remember stuff from grade 11, the difference between the two. Real gases, we know that real gases deviate from an ideal gas model at very low temperatures, right? And at very high pressures, isn't it? Is it so? I'm thinking about the issue of the temperature now. Yeah, I think that's what it's described. Is it at very high temperatures and very high pressures? Or is it low temperatures and low pressures? Yikes. I guess in bad. But you go and check that out, okay? I think I've forgotten now. In fact, before I miss my point, trying to think about that, I don't want it. So essentially, when the temperature is not ideal, so I mean, let's just say it's not where we expect an ideal gas model behavior of a real gas, of course, the gas particles themselves start to occupy a volume. Okay, so this happens at very high pressures. I remember that. But as for the temperatures, I'm not too sure anymore. My mind is just going astray right now. Anyway, you check that out, folks, so that there is sense to what is going on here. But again, this is just, pushing, the limits a bit because, as I said, precision is key in these questions. Right, so we do expect that the molar gas volume should be different. Now we need to calculate the mass of the impurities. Can you see? We're not calculating the mass of the pure stuff, of the impurities present in the calcium carbonate. All right, so we know that the total mass of the pure as well as impure is 15 grams. So this means we need to find out how much is the pure calcium carbonate in experiment 4. Sorry, the mass was 25 grams, sorry. So now we need to find the mass of the pure because the pure is what is going to react, right? And whatever has reacted is the pure calcium carbonate. So we will then subtract that from the impure, which was the total. Then it will give us the mass of the impure. So this needs a clear understanding, guys, again, of how this works. Of course, here's our equation. We were given calcium carbonate solid. We added 2 moles of HCl, aqueous solution. It produced calcium chloride, salt, aqueous, and water, which is liquid, plus carbon dioxide gas. Right. So we need to use this. Of course, we are looking at carbon dioxide, and we need to focus on the limiting reagent because this is not going to give us a clear indication unless we know how much of it was used. Maybe we would say this particular concentration was given at the beginning, and then this is the concentration at the end. So that would give us an indication of the number of moles used. But at this stage, there isn't anything, so we are to avoid looking at HCl for this purpose. But the limiting reagent is a direct indicator of how much of the product we will have. So of course, guys, we can see it's a 1-to-1 ratio. 1 mole of carbon dioxide is produced from 1 mole of calcium carbonate. So what we can see here is that we can easily say 1 mole calcium carbonate is producing or produces 1 mole of carbon dioxide gas. Right. So this implies that the number of moles of calcium carbonate used is going to be equal to the number of moles of carbon dioxide produced. Right? So this also continues to say calcium carbonate. This is the pure, by the way, because only the pure reacts. Right. Is going to be equal to, now the number of moles, we have the volume, so it's going to be basically the volume of gas divided by the molar gas volume, right? Right. So we continue, number of moles of CaCO3. Now what was the volume that we got? Is 4,5. Now this is already in decimeter cubed, so the units must be the same. So again, we were given that this should be 25,7. So we know that the number of moles of calcium carbonate is going to be the result. So let's get the calculator working. 4,5 divided by 25,7 gives us this 0,175 mole to 3 decimal places. Okay, that is the number of moles of calcium carbonate that was used. And of course, from the number of moles, we calculate the mass that we used. So we can say, therefore, the mass of calcium carbonate used is going to be, we know mass is number of moles times molar mass. This is from the equation, number of moles is mass over molar mass. At this point, we just want to go for the jugular, guys. So this is 0,175 times, what is, calcium is 40, carbon is 12, oxygen is 16 times 3. Okay, we need to think about that and get it done, guys. Right, so this is basically calcium carbonate is going to give us what? 100 or so. I think so. Is it 100? Or it's going to be in the 80s. I used to know this by heart. But let's see. This is 40 plus 48 plus 12. It's 100. Yawena, sayikhumbula. 0,175 into 100. So this gives us 17,50 grams of pure calcium carbonate used. Okay, and mind you, we used it all. We used it all. Ne? So we can say then, we know that the mass of impurities here is going to be the original mass of 25 grams minus that of pure calcium carbonate, which is going to be equal to, so this gives us a 7,5 grams. Okay, very easy, not so complicated, as long as we know what we are looking for and we know what to do and how to get around business. This is just key for this. As you can see here, it just says 7 grams here. I don't know what is the issue. Perhaps maybe the rounding off that we did could have been the issue. I'm not too sure. I'm not too sure because I don't see the reason why it has to be. I don't see why it has to be that small. But again, 7, guys. But for me to say 7 and yet this thing is 7.5, it's ridiculous, is it not? Let's see again. Maybe there's a mistake here. I had 4,5 divided by 25,7. That we multiply by 100. So this is still 7,5. I mean 17,5. And when we take 25 there from this, we know that we get 7,5 essentially, either to 1 decimal place or 2 decimal place. So this answer is incorrect. So not exactly correct, because 7,4 with a 9 before it to 1 decimal place is quite significant. So we cannot just rubbish that. Unless I am missing something, which, but I think the mistake by the examiners here was to not include, maybe they put 20 instead of 25. Let's see what happens. Let's see what happens. Okay. Let's see what happens. Okay, this is getting ridiculous. I'm just wondering though what happened here. Right. So that's the mass. And then let's see what happens when 20 is taken. Nah, it doesn't even work. So I don't know, perhaps there's a misprint. It happens sometimes, you know. It happens. Okay, of course, to maintain our 2 decimal places, which is usually the instruction, that should be okay. Okay, guys, so that's just the story right here. Not too complicated, but something that we need to keep in mind when dealing with these questions. Right, so what are we going to get here? Usually for the formula, folks, very important, substitutions, answer, and getting the mass of the stuff, and essentially getting the answer. Of course, these marks, guys, can be distributed however one chooses. At the end of the day, one of the formulas is going to get a mark. One of the substitutions, perhaps the substitutions are too easy here. But what was more important was the molar mass calculation over there, I suppose. Again, this is just me trying to find the common areas where marks are usually allocated. But remember, this could still hold a mark. Yeah. Or this formula can hold a mark. So there can be more marks created if one wanted to give more marks for this question, because it is indeed worth about 7 marks, honestly speaking. But at the end of the day, what we do is what we do. Okay. What we do is what we do. I wonder, what does that mean? Goodness. Right. You want us to take a second question? Maybe let's do 2 questions for each, you know, so that you guys can appreciate, you know, the things that need to be done. Do we have some big questions here? I actually like this question 3. It looks a bit interesting, don't you think? It looks a bit interesting. But question 2 as well, but my worry is that it's similar to what we have just done. But let's just answer this question 2. Who knows, guys, I can just limit this video to just this, you know. I can limit this video to just this section. and perhaps do another video for a different section, because I think, again, it helps to have a look at these sections, individually, rather than to combine them, because you end up losing focus, I suppose. Because I can see that it's getting a lot hotter. So maybe we can do 3 questions and then let you do the rest. And we get to the other topic again. We do the same 3 questions, and then you do the rest. And the last one. And then, of course, you do the rest. Because if I combine these videos, they become a long, tiring video, I suppose. But again, guys, it's nice to find things under one umbrella so that you can just, get stuff done without needing to search for the other videos. It's quite boring, but again, yeah, for the purposes of this last minute stuff, so perhaps it's okay to do this. Then you guys can just take your time, but I will also take my time in doing them, right? So I'll do this and perhaps take a rest, eat something, and then continue. Right. Now let's look at this one. It says, this was taken from March 2015. We're told that a group of learners uses the reaction of excess hydrochloric acid. Again, you see this one is not a limiting reagent with zinc. So this becomes the limiting reagent. To investigate factors which influence a reaction rate, this is our dependent variable. Now the balanced equation for the reaction is given. Great. So now let's analyze this reaction of ours. We see zinc is a solid, but zinc now has picked up the chloride. So this is more often, not necessarily an ion exchange reaction, but it seems to want to suggest that, because the HCl has actually lost that, but now it didn't exchange. Maybe when we say ion exchange, if we had zinc sulfate, now we end up with, sulfuric acid on the other side, whereas we would have, things like that, HCl and stuff. So that would be an ion exchange per se. But at this stage, would we say this is an acid-base reaction? Not necessarily. When a metal reacts with an acid, we often produce hydrogen gas. And usually this is a redox reaction. It's a redox reaction. And if we look at this one, this is the spontaneous type. Because if you just pour an acid and then you dip a zinc solid there, all you'll see is a reaction taking place, and you'll see gas bubbles of hydrogen gas coming out. So it's spontaneous. So if it is spontaneous, what do we know, guys? Delta H is less than 0, because spontaneous reactions are exothermic. Okay, again, how do we know this is a redox reaction? We look at the oxidation numbers. A solid has a 0. This time, chlorine has 1 minus, but there's 2 of them, so there's going to be 2 minus here. So we know that this 2 minus must be coupled with a 2 plus for this to be rather solid. Should we say stable? So zinc came from 0 to 2 plus, right? Now, as we can see, there's an increase in the oxidation number of zinc. So that is oxidation. But if we look at the hydrogen here, it's 1 plus, of course 2 plus because of the coefficient, whereas the chlorine has a minus there, again because of the coefficient, it's a 2 minus. But if we look at the chlorine, it remains a negative on either side, right? This is what we would call a spectator ion, right? But now the hydrogen from 1 plus, it goes to 0, because when it is in its diatomic state or natural state, it is a 0 or elementary state, right? So again, there's a decrease in the oxidation number. Hence, we call this a redox reaction. Oxidation and reduction took place in this reaction. So it helps to analyze these guys, because as I said, you never know when questions relating to that aspect are going to be popped. All right, let's look. We are told that they use the same volume of hydrochloric acid and 1,2 grams of zinc in each of the 5 experiments. Okay, the reaction conditions and temperature readings before and after completion of the reaction in each experiment are summarized in the table. Now we can see that experiment 1 uses 0,5 mole per decimeter cubed, and then the temperature before it was 20 but after it was 30. Can you see there is a definite release of heat because the reaction is exothermic. Right, the state of division here, we can see that we used granules here of zinc, and of course the time it took was 50 seconds. Right, it's quite a long time. So this is the slowest reaction because the longer it takes to complete, it's the slowest. As we can see, all the others are much less than that. But the sense into this was the fact that we used granules, maybe. And of course, a somewhat lower concentration of HCl. That's not a big deal otherwise. If we look at experiment 2, we're using the same concentration as in 1. And of course, the temperature before was the same, but this one went a step further. We got 35, right? And why did we do that? Of course, we look at this. We used a powder. And this took less time. Now, why is the temperature different? Why is the temperature different at the end compared to the other one? Remember, a faster reaction rate will complete much faster, so there will not be a loss of heat while the reaction is slowly progressing. So this one goes quick. So this is just to suggest that the temperature, when we achieve it, we sometimes lose it into the environment. So that would be the reason, because a slower reaction rate allows more time for the temperature to be lost into the environment. So that would be the sense into that. Right, experiment 3, we've got a higher concentration of HCl. Again, the temperature is the same, and we see that this is much higher. Again, we can see that the reaction is going to be much faster, so it's certainly going to keep the heat, or at least by the time we measure the heat, we will not have had enough time to have lost a chunk of that heat. As we can see, this is much faster. And then we used the same concentration of HCl as above. And of course, we see that the temperature was changed here. So that means we added heat. Okay? And now this is the independent variable between the two experiments 4 and 1. We changed temperature here. And of course, we know that that reaction is going to be fast. And we will see that the temperature after was higher, even though we used granules, but the temperature remained high because of that temperature, the reaction rate was faster. As we can see, this was like 8. So compared to experiment 1, this reaction is much faster. Why? Because the temperature here was the independent variable. Now, experiment 5, we see that again, we use the same concentration as in 1, same temperature before, and then we end up at 34 again. As you can see, experiment 5 is nothing but the same as experiment 1. But here's the issue. Temperature is different. I mean, the time is different. So what does that mean? Likely a catalyst, because a catalyst will only speed up the reaction and nothing else. So as we can see that, okay, the conditions are similar to 1, so we must have used a catalyst here. Okay, can you see, guys, when you analyze pieces of information nicely, you get the right ideas. You don't get lost as to, okay, why? You always think, and in fact, once you have read well and you understood things, we know that catalyst must be involved here for experiment 5. Because the reaction rate is faster than one, but it's more or less the same issues on the table. So there's something unaccounted for. And the likely one is a positive catalyst. Okay. Right. And it would be an opposite situation if we found that this experiment took longer than the first one. Then it would mean we have a negative catalyst. So think about these things, folks, as you go through these questions. Of course, take your time. Please don't pressure yourselves. It doesn't work. It doesn't work. You will be erratic. You only time yourself when you are confident. Until the confidence is high, do not do time attack. You will automatically perish in the exam. Don't do it. There's no point. It's like, for me, I always ask myself, if I am to perform an operation on someone, I ask myself one question. Of what use is this operation to this patient? Is it going to benefit this patient somehow? Is there any chance for a benefit for the patient? If not, the fact that I know how to do it and perhaps, can do it safely is immaterial. Because remember, with any little bit of action, there's going to be somewhat a reaction, perhaps a damage. So if the patient ends up being damaged and yet they were not going to benefit from the surgery, why should I perform the surgery? Yes, people can tell you, perform it, just do a small debulking, just take the tissue for biopsy. What is the point? Because taking that tissue for a biopsy is not going to help the patient, but it can help an academic cause for sure. And of course, an academic cause may eventually yield results into what this can be. But again, do we ever look at the fact that this is someone in need of help? And of course, if you are a person who sits down with the patient, you give options, you tell them also the impact that they could make, even though you cannot cure them, but they can cure many others in the future if we get this right. Will they consent to this surgery, perhaps just a biopsy? So we can do studies on these and perhaps try certain treatments and see if these can be good for the future. Of course, they themselves, if they live long enough, may be the beneficiaries if the answers come early. But again, this is not a very definite type of a situation. It's more of guessing if things go well. But you'll find people just trying to push a family to accept a biopsy, although knowing very well there's no oncological therapy that's going to be useful for this person. Even if they find that the tumor is aggressive, it's one of those malignant types, they will not be able to go back and operate again. So my question is, why operate in the first place? Unless, of course, the patient themselves say, look, do whatever you can. I would rather die having tried than not. Then that's fine for me. That gives me confidence. Of course, I'll still exercise the surgery the way I know how, but I know very well that here, my patient fully understands the benefits and risks, and again, even the impact that this can have on their quality of life. Also, on the positive side, what this could have, to many others in the future if we find answers due to this exercise. But again, this is the same with studying, folks. With studying, you either decide, if you're preparing for an exam and you feel not ready, yours is to do your best in the exam, right? Because there's a chance you might just get it right, but you know very well the chances of failing that exam are high if you're not prepared. So timing yourself is not going to make a difference. It's a waste of your time. But again, it's up to you, right? It's up to you. Because you cannot time yourself without knowledge, man. It's pointless. It's like a runner trying to time themselves to beat a particular time record, when they are not fit. How ridiculous is that? What's the point? But someone who is fit, who did the endurance training first, then that person can push themselves to the limits because they're already fit. So they stand a very good chance of beating, any time records set in the past. But you can't do that if you have not built your endurance. It's I don't know, guys, but it really freaks me out to see people, doing things that are not beneficial to their very own cause. But again, it's all this misinformation and disinformation, just inaccurate information. Because you see, it's easy to believe, guys. Don't get me wrong, I'm a believer. It's easy to believe things you have not seen. We call it faith, right? But there are certain things in this world God created to be a reality. And we cannot get around these with this mindset of we need to believe. Remember, faith is believing in things unseen, isn't it? But now science is what you see. So are you trying to tell me that now this idea of faith, you would want to apply it to science like that? No, it's inappropriate. Remember, it does work, but not in this scenario. But God can perform miracles anytime He chooses. He's proven it to all of us that He can take even the lowest of, the low people and make them the highest of all high people. He has done that with Daniel. Daniel was not initially a person who interpreted dreams and stuff. The people who did that were known. They are the what we call traditional healers, which I don't understand. What do we mean when you say traditional healers? Because do you want to tell me that a doctor is not a traditional healer? That's just the thing. Do we ever understand what we talk about when we say traditional? What do we mean by that word traditional? Because those people are healers, both of them. And in fact, they are traditional healers in their own right. Because if we call it the Western tradition, a doctor, it traditionally is a healer. In an African sense, our gifted people, I would put it that way, are healers. Because we face different challenges sometimes. And of course, there's more challenges of a different nature for a different group of people. But again, you see, the civilization has somewhat created a more equal type of a situation because we start to face health problems that are similar. Because we tend to eat similar foods now because we are trading foods amongst our countries. So whatever they eat in the US, we eat here as well. So whatever problems they will have as a result of that is starting to become a problem for us too. We watch how they behave on their movies and what, and we're starting to replicate that in our countries. Now there's violence here that is uncontrollable, so we suffer the same fate in a way. But let's think about things, guys. We need to do what is necessary than what is unnecessary. At the same time, what is necessary may not be relevant in a given situation. So we need to be able, again, be situation specific, I suppose. So you cannot tell me that you will fail to study your books and then you will pray that you will pass the exam. That's ridiculous. You're already actually insulting God Himself if you do that. But if you do study and you get your stuff in shape, yes, you may have challenges of, that solid understanding. You can pray then that God gives you enough wisdom to exercise that which you've already studied, and of course, give you an edge where there is a chance. It happens, you may pass. But if you don't do your work, you are not diligent, praying is a waste of your time because it's not going to work, okay? You can pray and cry, fast all you want. You're not going to make it. Unless it's God's plan to make a statement about that. But until then, it's not going to happen because you want it. It's only going to happen because He wills it, right? So we need to be very clear, guys. I don't know why I'm going on this preaching spree now. I should not be preaching because you know what? Time is money, guys. I want to spend at least 2 hours on each topic and that's it. So this is going to be a total of 6 hours of me talking to you folks. So stay with me. Of course, you may jump off if you feel this is overwhelming. Right, let's get to this question. It says, is the reaction between hydrochloric acid and zinc exothermic or endothermic? Do you see what I mean? Do you see what I mean? Can you see there was no indication of anything like delta H? So if you did not understand what's going on, you would not know what's cooking here. Of course, those who are fortunate who have, who have done experiments on these, they would know it's exothermic, and essentially they would have some justification for this. So it is indeed exothermic, okay? But you may talk about delta H here, if you will. Is there any place where there is a mention of this? No, we just had to know it. Right. We just had to know it. So do you see how these classes, guys, are so useful? Because some things, it's just, the essence of the science. Having gone through the rest of the topics, it makes sense now to understand what's going on here. But you will not necessarily see it like this under normal circumstances, but you have to come up with it. So we know that this is exothermic. It's exothermic. Why? Because it is a spontaneous reaction. That released heat. Heat. Okay. That's very important because the evidence is here, actually. But again, they made it too easy. Sometimes you may not have this. You would have to know from just, the revision that we did before we got in here. But the key thing here is that this is a spontaneous reaction that released heat, because we saw that heat from the beginning and the end was not the same. So that means we released heat as this reaction progressed to its finish. Right. Okay, we can even say as it progressed to completion. Sometimes answer in such a manner that no follow-up questions get asked. The answer has to be as complete as possible. As it progressed to completion. Right. So that's it, guys. Very nice and tasty stuff. As we can see on the table, of course, the evidence is there. Each of those reactions released heat. So 2.2. What do we have now? Give a reason for the difference in reaction rate observed for experiments 1 and 2. So what did we say was the independent variable there? Experiments 1 and 2, the only difference was that we changed the state of division. Right? For 1, we used granules, which provides a lesser surface area. And in 2, we provided powder, which provides a greater surface area. Okay, so basically, the reason here is a greater surface area for experiment 2. So we can say 2 has a greater surface area than in 1. That's it, because powder provides a greater surface area. But you can't just say powder. We need to hear this thing. It's all about the surface area available to collide with the HCl molecules. Right, so that's just 1 mark, nothing big. 2.3 says, the learners compare the results of 1 and 3 to draw a conclusion regarding the effect of concentration on the reaction rate. And of course, we can see there that 1 and 3 differ. But this is a dangerous comparison, right? Because if we look at 1 and 3, it's not a fair comparison, right? Because we have a different concentration of HCl, and we're using powder as well. So those two, no ways. It says give a reason why this is, oh goodness, that's good. It's because there's more than there's more than one variable that differs. Okay, they differ by more than one variable. You can say the two experiments differ by more than one independent variable. In this case, it's concentration of HCl and the state of division of zinc. Right, so that is an unfair comparison because there's already an advantage by just the change in state of division, and essentially the concentration becomes an added advantage, so it doesn't make any good comparison. Right, so this is 2.4. 2.4 says, how does the rate of the reaction in experiment 5 compare to that of experiment 1? Write down faster than, slower than, equal to. Okay, so it says write down the factor responsible for the difference in the rate of reaction and fully explain by referring to the collision theory how this factor affects the reaction rate. So again, you can see, guys, back in the days, questions had to be much more structured and there were more marks for these explanations. Lately, it doesn't seem to be the case at all. It's usually very direct questions where you just put 3 bullets and that's it. But here, can you see we need to write first slower than or equal to, then we need to write down the factor that is responsible for the difference. Again, this is just another way of the examiner is giving a structure to this argument, as we have stated at the beginning of this video. Right, okay, so experiment 1 and 5. We can see that experiment 1 and 5 are essentially the same as we said. But the reason that this is faster, we see it on the time of the reaction, okay, the reaction time. It's slower, so it is essentially faster than. But now we need to write, yes, of course, we looked at that this is likely an issue of a catalyst. And we can use the collision theory to then explain how a catalyst influences a reaction rate. Right, so we're going to say faster than. Okay, it is faster than. Due to the use of a catalyst. Usually we talk of a positive one rather than a negative catalyst. So due to a use of a catalyst. So can you see we already have 2 marks in the bag. Now we need to discuss how does a catalyst influence a reaction rate like that. So we can say a catalyst lowers, don't know what I'm doing there, lowers the activation energy needed for the reaction to take place. Okay, this allows more molecules to have sufficient kinetic energy for effective collisions per unit time, right? Hence, a higher reaction rate, right? So that's it, guys. It's just those 3 bullet points. How does this do the job? The mechanism. It lowers the activation energy. And what is the influence of this? It means more molecules will have sufficient kinetic energy for effective collisions per unit time. And that translates to a higher reaction rate. Okay, so that's the essence of this. Of course, guys, we get a mark for explaining the mechanism. And of course, the end result of that there will be sufficient kinetic energy for the molecules, as well as effective collisions per unit time increasing. Okay, sufficient kinetic energy for more, maybe let's put that out, because there has to be more effective collisions rather than just effective collisions. Come on, man. What are you doing? Kanti intoni nangalo P? Yewena P, senihlanyisa wena. P ofuna undiqala kabi. So for more effective collisions per unit time, hence a higher reaction rate. I don't know, guys. Hey. That's the one. Of course, one may say 2 marks for that statement, or may even come up and give a mark here. But again, since we said faster than, it already translates to a higher reaction rate. So as you can see, these 5 marks, guys, are not too bad. But again, one had to really think creatively and constructively and reasonably. Because you cannot have unreasonable thinking here and expect to get the marks. Okay, right, let's do the last one. So the last one says calculate the rate at which hydrochloric acid reacts in experiment 4. Can you see it is stated how we are going to write the unit? This is in mole per second, and we're already given the answer here, so we need to get something within a certain range sometimes because of the accuracy of how we're going to do this. Okay, 6 marks. Right, so we want to calculate the rate at which hydrochloric acid reacts. Okay, so that's what we need to look at. So how are we going to do this, folks? Because we don't know how much of the product we have made. So this is quite taxing, is it not? But again, we can use the limiting reagent, because the limiting reagent will then help us by using the molar ratio. So we can use the limiting reagent to then find out what would be the rate of the partner. But again, this anchors on the molar ratio. This is a very good question, by the way. This is a very good question, okay? So this is not so difficult otherwise, because we just need the number of moles, then calculate the rate for the zinc, then use the molar ratio to then estimate the rate for the HCl, because we don't know what was the start and the end for that, so we cannot use it directly. So we have to use the zinc as a surrogate to then get to HCl. So let's try to put it in here, 2.5. So of course, guys, from the equation, we saw that zinc reacted with 2 moles of HCl aqueous to form zinc chloride, salt in solution plus hydrogen gas. Right, that's what we got. So we know that we don't know much about the products, but we do know about zinc. At least we know what started this whole process. So its change is going to be in effect. It's going to give us an indication of the reaction rate. Okay, so we can say, okay, fine, we know that the number of moles of zinc is going to be the mass that we used for experiment 4. So what was the mass? We were told it's 1.2 grams. Now we want, it's going to be the molar mass first. The mass divided by the molar mass. Okay. Right, so this is going to be 1,2 because we're told we used the same mass. The molar mass of zinc, where is the periodic table? I don't have one close by. Okay, let's see. Luckily I have a chemistry paper next to me. An old paper, so let's see. Okay, zinc is 65 according to the periodic table that I have. Of course, they may be different for the one given in a particular exam, so don't cram these values. Take them from the information sheet. This is what you would want to copy as it is, because it may differ as written there, so be very careful. So we know that we are getting a number of moles, which is 0,018 moles, right? That is the number of moles of zinc. Now, folks, we want to calculate the rate at which zinc is being used. And remember, we're using reactants. So you can say the rate of reaction with respect to zinc is going to be minus the change in the number of moles divided by change in time. This implies that the reaction rate with respect to zinc is going to be minus the number of moles. They will end up being finished, right? So that is what we're going to have. But there was an 8. Goodness. You know, things just like to go wrong. Please stay awake, guys. I know when the examples are too long like this, it sucks. So that was 8 minutes. So 8 minus 0. So we can say, therefore, the reaction rate of how zinc is being used is going to be the number of moles divided by 8. Right? So this gives us a 2 times, this is 2, 0, 2,31 to 2 decimal places times 10 to the minus 3 mole per decimeter cubed per second, because we're talking about times in seconds. You can write it like this, or you can write mole per second. Doesn't matter. Now, folks, that's not it. That's not it. We can say then, we know from the equation that 1 mole of zinc reacts with 2 moles of HCl. This implies that the reaction rate with respect to HCl is basically just going to be 2 times the reaction rate with respect to zinc. Therefore, the reaction rate of the use of HCl is going to be 2 times 2,3, 1 times 10 to the minus 3, which is, let's see, we just double this. So it gives us a 4,62, getting a 4,62 times 10 to the minus 3 mole per second. Okay, right. So that's it, guys. So we can use the molar ratio, or we can use the number of moles of zinc to find the number of moles of HCl that we used. Okay, but the problem is that, of course, the one that we used is the change, isn't it? So that would be okay as well. And then we calculate the rate the normal way. So here we've got 2 options. It's either you calculate the rate with zinc, or we use zinc in terms of number of moles to find the number of moles of HCl. Once we have the number of moles that were used, that would essentially be what would have been the change. So we can divide that by essentially the time, and that should give us the answer. As you can see, we got 4,62 instead of 4,63. Let's just try to perhaps use the number of moles of zinc to then find the number of moles of HCl. We can say therefore the number of moles of HCl would be 2 times 0,018. Let's see what we get. So we've got 2 into 0,018. So this one gives us a 0,036 moles, okay? And of course, if we then perform the calculation using HCl, this is what we would have to do. So the reaction rate in terms of HCl would be negative, the change is going to be 0,036. Remember, that is the change. That's what we used essentially. That's going to be the change from initial to after we have used, or final, so to speak. And then the time frame was 8 here. Let's see what that gives us. This divided by 8 is 4,5. 0 times 10 to the minus 3 mole per second. Okay, this one is even smaller, but again, it's not bad. It's because of the rounding off. So I think either way, that answer would not be incorrect, it would not be incorrect. So essentially a range of answers would be, somewhat relevant. But again, the issue of using molar ratios is, quite an important thing. I think number of moles is important. Molar ratios are important. Yeah. Before I start mincing my words, folks, what are we doing here? So of course we can say perhaps getting the mass of zinc was key. and the number of moles. The formula is not really key. I think the key formula here is the one in question, and then calculating the issue right here. That's 4 marks. And then finally getting us where we need to go is key. So this is how the 5 marks, I believe, is to be scored, folks. Otherwise, the rest of the other gymnastics are a means to an end. In essence, we would not really attach too much importance to them than we would what preceded that. Great, so that's it, folks, for that question. As you can see, guys, there's not a lot of difficult questions here, but precision is key. Okay, folks, I would like to perhaps you know most guys, sometimes it helps to just stop. But again, why not take an extra example so that you guys get to appreciate this. So this was March 2015. Now we've got June 2015. What I like about this question is that it has a bit of a graph, and in fact graphs within it. So perhaps it's a good one to look at as the last one of these questions. And then you guys can go on practice for, do the rest. There's plenty of questions. You can see there's lots and lots. And others you can recognize from previous exams. There's lots and lots and lots of questions here. All right. So try to exhaust these during practice so that you can get better and better. Okay. You see there's lots of questions. And then of course we get to the next topic. So there's more than enough for you guys to practice. My job is just to show the way. And once it's shown, you guys have to walk the way, isn't it? Yes. Okay, let's take down this question 3 as the last one for this. Okay, so question 3 says a group of learners uses the reaction of clean magnesium ribbon with dilute HCl to investigate factors that influence the reaction rate. It's almost always the case here. That's our dependent variable. Now the balanced equation for the reaction is magnesium, HCl, forming magnesium chloride and hydrogen gas. And we know this is a redox reaction. I'm not going to take you through that. And it's an exothermic reaction because it's spontaneous, right? Right. So of course, we are asked the question to decide this. So we go for it. 3.1, we know that this is exothermic. And of course, we're told to give a reason. We can see that essentially delta H is less than 0. There's not a lot for us to say. Exothermic, delta H less than 0. Can even go on and say this is a spontaneous reaction at room temperature that releases heat. Right. So 3.2 says in one of the experiments 5 grams, can you see in one, not all, 5 grams of magnesium ribbon was added to the HCl solution. Now we don't know which one is the limiting reagent here and which one is in excess. Nobody told us. So this is very interesting. Excuse me guys, my throat always misbehaves when I'm doing these videos, and yet I don't do this under normal circumstances. I don't know why. Or maybe it's holding this tablet affecting how my glands work and all that, because honestly these gadgets, guys, have an influence on the nervous system. It tends to function less when holding these gadgets. Maybe that's the thing. I need to learn to use it on a surface or so. Okay. Yeah, Yeah. So the question 3.2.1, right, says if 30 centimeter cubed dilute hydrochloric acid solution of concentration 0.5 mole per decimeter cubed is used up. Can you see? Used up, meaning we know enough whether it's in excess or not. But if we know that that particular volume of that particular concentration got used up in 1 minute, can you see we're given time as well? Calculate the average reaction rate in moles per second. Right, so this one is much easier and straightforward. Of course, we know. But at this point, I doubt we need to use the molar ratio because nobody asked us in relation to which reactant or product. So in essence, we use what we are given. So we know that, okay, all right, we need essentially the number of moles of the acid. So we know that the concentration itself, we know that concentration is basically number of moles of a volume. So we were given the concentration is 1,5 equals number of moles, which is what we want. Volume was 30, so this is going to be 0,03, isn't it? Because we divide by 8,000. So 30 divided by 8,000, we get 0,03. Okay, that's good. So we know that the number of moles of HCl used is going to be 1,5 times 0,03 when we cross multiply. So we time this by 1,5. We get 0,045 moles. Right. Now that we are done with that, remember what is used is the change. Remember that from what was initial and what is final. So we can say then, we know that the reaction rate is going to be minus, since we're using a reactant, change in moles over change in time. So this gives us minus into essentially 0,045. We then divide this. As we can see, this is per second, right? In moles per second. So 1 minute is 60 seconds. Again, that is key. So let's see, that divided by, in fact, why do I do this? At this point, we know the change is given in a positive sense, so to speak. Or if this is used up, so that's going to be 0 at the end minus that which got used up. I'm thinking about it. The negative is not necessary here, honestly speaking. It is not, and it's a waste of our time. Divided by 60. So this gives us 7,50 times 10 to the minus 4 moles per second. As you can see, guys, the answer is perfect for this one. So again, these questions may look very scary, but they're usually not so bad compared to the ones for chemical equilibrium as well as acids and bases. Okay. The formula that answers the question, converting that to 60, that's the mark. Okay. And then of course, converting this to decimeter cubed, and the answer gives us the extra 2 marks. Okay, that's very important. Substitutions per se, if we want to push it to 6 marks, we can give, but there's no need. And if we want to push it to 7 marks, we can give even the formula for concentration. So when you see a lot of marks in this particular question, it's normally on the detail rather than to say this is an impossible thing to do. Okay. Right, so we've got 3.2.2. Now for 3.2.2, we've got a few issues as well. A says, how does the rate of the reaction change between, right? Oh, we didn't read. The volume of hydrogen gas produced as a function of time in this experiment is represented by the graph below. The graph is not drawn to scale. Fine. As we can see, the reaction started a bit slow. Then between T1 and T2, it became very steep. And then between T2 and T3, it started to even out. And then the reaction stopped. Right. Right. So, it says, now how does the rate of the reaction change between, write down, increases, decreases, or no change between T1 and T2? Okay, so what is going? It says, then use the collision theory to explain the answer. Ho, 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 ho. Hot, 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 chilly stuff. Okay, how does the rate of the reaction change between, all right, not a problem, between T1 and T2? It is quite explosive, isn't it? It increases, because we can see the gradient if we draw a tangent here. That one, and then it gets very steep, can you see? So between T1 and T2, it's increasing, so it increases. Okay. Important, increases. Now we need to explain using the collision theory. Why is it increasing? Remember, this is an exothermic reaction, right? So when it starts, the temperature is low, isn't it? But because now it's going to release heat, it kind of self-drives. That's why exothermic reactions actually drive themselves to completion. It's because it produces the energy that essentially speeds up its very own reaction. Because that heat, a part of it, before it's lost in the environment, a part of that heat is going to be essentially influencing the rate of that reaction by increasing it instead. So I like this graph because it's more of a natural and sensible phenomenon. Okay, so we can say, okay, safely it increases. Now why? We can say an exothermic reaction releases energy, okay, in terms of heat. Now an increase in temperature will speed up the reaction by making sure that more molecules have sufficient kinetic energy for more effective collisions per unit time, and hence the reaction rate increases. You will see that it's quite an explosive increase once the reaction starts. Okay, so we can say here an exothermic reaction releases energy by increasing, releases heat, maybe, let's say that it releases heat, releases energy in terms of heat. Okay, maybe let's put it that way. Heat. That is an increase in temperature. Okay, which will in turn increase the kinetic energy. Kinetic energy of the reactant particles, so that, okay, maybe let's not say too much, a long sentence, it's going to be boring. So we can say an exothermic reaction releases energy in terms of heat, which will in turn increase Okay, maybe let's not say in one word. Let's just say an exothermic reaction releases energy in terms of heat. That's bullet number 1. Bullet number 2, we can say this will increase the kinetic energy of a reactant molecules, right? And we can say more molecules will have sufficient kinetic energy to form effective, oops guys, maybe to form more effective collisions, to form effective collisions per unit time, right? Hence, an increase in the reaction rate. Okay, hi guys. Thenga ndiyabhayisa ngo. Thenga nibhala kabi nje like period. Thenga le tablet seyandihlanyisa ngo. Okay, ndiyimvelo bhedayo but ngizoblame i-tablet. Anyway, hence an increase in the rate of reaction. Come on, man. Rate of reaction. Okay, right. So that's a lot to say, but we have explained it, guys, in the best way possible. So we score our marks here. First mark is for choosing increases, and then stating that their exothermic reaction releases heat in terms of, energy in terms of heat. This increases the kinetic energy of reactant molecules. Then more molecules will have sufficient kinetic energy to form effective collisions per unit time. That's a mark, hence an increase in the reaction rate. But again, this is more of what we have already said and got a mark for. So I believe the mark is here. Okay, so again, you always look at what is stronger in terms of getting the mark. At the same time, structure your argument in a manner that protects you. Okay, guys, so I hope this is clear. Now let's look at B. B says T2 and T3. It says give a reason for the answer without referring to the graph. Okay. Oh, that's strange. So what's the rate there? It's slowing down. Okay. But now how do we give a reason? Now we cannot use the gradients that they are evening out. So we'll say it decreases. Now we can say why? It's because there's less reactant molecules per unit volume. So this is going to be because there's less reactant molecules left per unit volume. Leading to less effective collisions per unit time. Okay, again we can say hence a decrease in reaction rate. Of course, guys, I'm singing. Some persons may just say it's because the reactant molecules are used up or being used up, so there's less available for effective collisions. How you phrase it, folks, doesn't really matter if it makes a scientific sense, okay? Because you don't hold a gadget that reads the mind of the examiner and what answer they have on the memo. And there's no point in trying to replicate that directly. This is why I should rather teachers, encourage the independent thought of a student. And remember, guys, to teach, it's not something that is easy. Don't see that the country doesn't recognize teachers as well as it does other public servants. Teachers are supposedly, the top of them all, because these guys produce engineers, doctors, presidents, you name them. All of them come through schooling. So it takes the teacher's skill and love for the job to produce such individuals. So these people should actually be earning more than anyone else, because they are doing the harder part of doing things, raising children of other people, ensuring that they become as polished as ever by the time they graduate from school. So technically speaking, guys, the teaching profession is not easy. It takes a calling, it takes passion, it takes love and enthusiasm in teaching kids with difficulties in understanding things, but to convert them into individuals who are independent in thought. I don't like the way this situation seems to be currently, where students are essentially propelled and even pushed into regurgitating some exam guidelines, which for me is a low. That's just a negative I can say about this curriculum, because besides all of that cramming and regurgitation that is encouraged, the whole thing for me is good enough for a student who is aspiring to become something greater in the future. Of course, with everything, guys, there will always be some negatives, right? It's not always positives, but of course there's more positives in this curriculum than negatives. All the others would just keep talking absolute rubbish, because those people are themselves failures. Remember, failures always try to hide behind something. They will blame something rather than themselves. And that's the sad part, because those people are the loudest. They talk more than those who actually are the smartest and the reasonable ones. We always have noise. This education system is weak. We need to make it important. We need to copy this so-and-so country, because that so-and-so country, you see kids at this particular age are able to do that. Think about it. It's usually torture to those kids. That's why they become ruthless and brutal individuals. And you will see that when there is some sort of a criminal, or should I say a crime committed by those so-called excellent countries, we say, it's usually an atrocious type of crime, because those people have never had a chance to grow normally. Even at their tender age, before they could appreciate the world around them, they're already made into workers. But again, if you compare their standard of living, these very people we praise so much, it's not so different from ours right down here. Sometimes you may even start to see that they live far more poorly than we do, although they make money for their countries, but it only goes to the elites, because an average person there doesn't really have a better lifestyle than we do. Actually, they have it much worse, unfortunately. But again, guys, you need to travel to see these things. Don't just hear reports by ignorant people who just assume things are that way because it seems to look like that on the face value. Look behind the curtains. You will see more ugly than what you think you would expect by seeing what is in front. Everything is mostly a front, folks. It's never the reality. The reality is far too much ugly, or uglier than what you see at face value. So again, guys, for me, please, folks, allow kids to be independent in their thought. Allow them to express their understanding of the subject matter. because that is how we can gauge how well we are teaching. But if we force them to regurgitate, anyone can do that given enough time to practice that. But it doesn't mean they understand. And that means these people may not even find value in doing this. This is why you go around, you find people saying, why did I have to solve for X in maths? Because as a doctor, I'm not solving for X. Okay, you think so. But you don't know what you're doing with the X. X is actually a placeholder, guys. It's nothing but a placeholder. It stands for something. Now, if you're giving a drug to a patient, you know that you're supposed to give a particular amount because the distribution of that drug in the blood is going to create a particular concentration over a certain time frame. Now, you don't want to surpass that because it will lead to side effects. You also don't want to be under that because then that would mean the patient is not going to benefit from the treatment. Now, to calculate how much you should give, remember the formulations are not ready-made for your patient specifically. And mind you, we need to weight the patient. I mean, to weight the drug so that the patient, we can consider the weight and the body water of the patient so that we can estimate the distribution of that drug and the concentration thereof. Now, you will have to use X, unfortunately, because if you say you've got a vial that says 20 mils has 20 milligrams of the drug, and now what you need, you want to give 5 milligrams of the drug, you have to estimate how much volume of that 20 mils are you supposed to give to this patient. And guess what? To calculate that, it's going to be solving for X. Okay? So you can go around the big heads thinking maths is not relevant. It's only because you are ignorant. Okay? Don't say it doesn't apply. It's your ignorance talking. And please be very careful of the nonsense that you spew around, because you are actually leading to more ignorant individuals. Please let them be ignorant on their own. Don't influence it if you are one such a person who does those things. And if you are confused as to why you are doing maths, solving for X, and doing all these graphs, you will understand when you become a professional. Keep an open mind, of course. But if you close it down to just doing these things as a means to an end, you'll always be one of those who say, in my 8 years of life, I had never used anything involving a quadratic equation. So these things are just meaningless. It's a scam, this education. Should be taught how to, how to do word work, fix engines. Well, yeah, but then every time there's a change, you will still need to be taught again, right? Because you won't be able to see how things work together. But those who learn the science first, they even know what's wrong with the design that they'll be working on in the near future. And so they keep on improving it and making it more efficient, more cheaper, and even more strong and durable because they understand the science. And it's those people who solve for X, even when others don't see the X. Okay, all right, okay. That was just a rant. Please don't take too much offense from it. But again, unfortunately, it is the reality that we face. I've got lots of people who don't understand why they studied chemistry. Because I don't use that. I just get a tablet. Who do you think made that tablet? How did they know you could make that tablet? Chemistry. Even what we call pharmacodynamics, what the body does to the drug, is essentially chemistry, right? Because the body is chemistry, guys. So you need to know these things. So what I'm giving you now, you better remember it because it's going to hurt at university. You will still be doing chemistry. But this time it's going to be a lot more difficult than it is for grade 12. That I can assure you. It makes a little less sense than it does in grade 12. But the problem is because you don't have time to appreciate this at university. And again, it's a lot of work at once. You'll be writing a test on 5 chapters of chemistry, your first test. You'll probably have finished 5 thick chapters. A chapter that is as thick as your book. that you use for grade 12 for the entire year. You'll be studying it in 2 weeks or even in 2 days. And then the next one. In fact, 2 days. In fact, 2 days is even too much. See, a lecture, if you've got a double period at university, a lecturer can finish 3 chapters in those 2 periods. If you look at those chapters, guys, they're as thick as your textbook that you use for matric. Okay, maybe I'm exaggerating it. Perhaps a quarter. Each chapter is almost a quarter of the textbook that you use, okay? But again, the reason is because usually those textbooks are very thick with very thin pages and very wide and big pages and a lot of text in each page. So in essence, if you were to combine that, that would be more like a quarter of your matric book that you use for the entire year. That's one chapter. And now there's going to be like how many lectures? Maybe 4 or 5 before your first semester tests, or should I say the first test for a particular section. And you find yourself writing on 5 such chapters, and you're only writing for 100 marks. So this means, guys, it's going to hurt if you don't know. It's going to hurt if you don't do your work. It's going to hurt badly, badly, if even the lecturer or the professor who teaches that particular subject likes to test knowledge rather than regurgitation. Of course, you do get weaker lecturers who, after all of that heavy exercise, just ask you easy questions on just remembering, regurgitation, sometimes repeating a lot of the past exam questions that have been written at the university. So some may think, okay, I understand university chemistry, but they actually don't. But you get ones that we had at my university. Man, it's like they were trying to prove a point, but of course they were right. You cannot be a university student and you're just there to regurgitate textbooks. No, you have to portray understanding and flexibility, because that's the essence of university training. We are training a professional of the country, okay, someone to solve our problems as a nation. Although you may sit in a corner somewhere at an office of a particular company, you would be thinking that you have less impact. You have no idea. That company has a wider and much larger reach. So if you are part of that company, that means you are part of the solutions for our nation, or even nations. Anyway, guys, I will talk and talk and talk until Jesus comes back. But at the end of the day, we've answered this question. No. There's less reactant molecules left, as the reaction progresses or they're being used up. And of course, try to be complete though. You don't want a question to be asked again, but if you're saying there's less reactant molecules, so what? Does less mean less reaction rate? Not necessarily. Okay? Be very careful of such answers. This is why you want to go on and say there is going to be less per unit volume, meaning the volume is much larger than what you have as the reactants. Now, can you see, this is already suggesting that now there's sort of like, an impact now on the reaction rate. But if you're going to have less in terms of numbers, but the unit volume is actually much smaller as well in proportion to the less you have, the reaction rate will pretty much be the same, So try to be as complete as possible. Sometimes quick answers are all attractive, but they don't make sense, okay? But these long, lanky answers, sometimes they look all unnecessary, but actually they drive the point home much better. Right, okay, guys, let's get to this one now. It says 3.3. Hey, guys, it looks like this video is only for this question, hey? Anyway, let's just keep working, guys, and not worry about time at this point, because I hate to do small little videos all the time. Now, in another experiment, they add 5 grams of magnesium. Can you see? We used how much? 5 on the other, and then now we're still using 5 again on another. Right, to 30 centimeter cubed of hydrochloric acid of concentration 1,5. Can you see here we're being given exactly how much acid? So this seems to suggest that the acid perhaps is the limiting reagent. But how would we know? We can calculate the number of moles of acid available in here. And we can calculate the number of moles of the magnesium. And of course, the lesser is going to be the limiting reagent. So this is very interesting, right? Okay, so they obtained graph T. Remember, this was graph S, the original. Now we've got a graph T. Okay, the graph is not drawn to scale. It says now give 2 possible reasons why graph T differs from graph S. Can you see, guys, what we need to appreciate here is that, do you see that for the first reaction that we used, which produced our volume S, sorry, our graph S, what did we have? 1,5 mole per decimeter cubed of HCl and 30 centimeter cubed of HCl, right? And 5 grams of the magnesium ribbon. Now we're doing the same here. 5 grams of magnesium ribbon, 30 centimeter cubed of 1,5 mole per decimeter cubed of HCl. But we're obtaining a graph that is much steeper. Of course, we can see that the amount of the gas that we get is the same, but that is a much faster reaction. So what happened here? Of course, if we have the same conditions and yet we obtain a much faster graph, it may be that we are using a catalyst. That's possible. Okay, we may be using a catalyst. And it may be that we've added heat as well, because we know heat can increase the reaction rate, as it will do it itself. But if we added extra heat, this can happen, because we cannot talk about, a different concentration. We cannot talk about a different state of division. Oh, possibly. Instead of using the magnesium ribbon, as was indicated, it could easily be powder, because then that would be a much faster reaction rate. So the issue here could be we've used a different state of division of magnesium, meaning powder, or we may have added heat. Despite this being a spontaneous reaction itself, we may have added a catalyst as well, because everything else seemed to be similar. So again, it says give 2 possible reasons. That's all. We did not need to explain here. So we can choose any 2. We can say we may have used, we can say Mg powder may have been used. Temperature may have been increased at the start of reaction, right? Yeah, what can I say? I want to write well, guys. Temperature may have been increased at the beginning phala kanjani kani? Hey, khawulezisa man. Beginning of reaction, and of course a catalyst, a positive catalyst. Could have been used. Okay, you're writing amimbi, guys. So it could be a catalyst, could be a temperature increase. We may have used a state of division of the magnesium that allows a larger surface area, saying that the mass of magnesium used was the same, the acid was the same, volume as well as concentration. So those are the other 3. Of course, you can pick any 2 of the 3. This I would choose, that I would choose. Even that I would choose. Okay. All right. So again, guys, this sums up those nice 15 marks for this question. Okay. So seeing that, guys, we are doing very well. Maybe let's take one more example, because there's plenty of examples. Let's just pick one more. And hopefully, guys, you're going to understand what's cooking here. Okay, guys, so let's take the last one. This is November 2021. My thing refuses, 2022, sorry. So this is one of, the not so far away question papers. Just to emphasize the fact that, guys, you need to look at question papers from old and question papers in the recent past and the most recent question papers that you've seen. Okay. Of course, guys, as you can see, the number of hours here that are going to be spent on this is ridiculously long. So I may try to perhaps squeeze in, issues of chemical equilibrium. But again, I don't want to make the video too long. But anyway, let's see what we can do in 6 hours. I think that should be okay. Whatever we can do in 6 hours, I will try to be as precise as possible and not to relax a lot. But so far I just need to eat or drink something quickly, and then we can carry on with this question. So do something. You can pause the video, try to answer these questions yourself, and see how this works out. But as I said, I'm going to provide this ugly memo of mine together with this document, guys, for those of you who will need to practice this. Obviously, this video is going to premiere a day after this production. So today is Saturday. So by the time you see this video, it's going to be Sunday, right? But I'm going to try to make sure it premieres early on Sunday so that you guys can have enough time to look at what I have presented here, and also have ample time to practice these questions. So what I like about this paper, it has all questions from organic chemistry to electrochemistry, and there's memos attached. In fact, there is a booklet at the end which has, worked solutions for each one of the questions, be it an explanation or a calculation or whatever. So in essence, guys, what I'm trying to say, you can use this booklet alone to revise tomorrow, as in today, because you will see this video today, but I've produced it the day before. So essentially you can use it only and not anything else. But of course, do remember to look at some definitions, look at some recent question papers, because sometimes you see examiners from different provinces can steal an idea from a May-June question paper from the EC and plug it in the trial in Mpumalanga, for example, and vice versa. So it helps again to look at what is available from different provinces. This is what I would rather you guys do. You see, instead of having all these stupid followers on TikTok and whatever you call it, useless followers, by the way, who don't really add any value to what you're doing, but they just cheer all the nonsense you do. Rather have people from different provinces who are your true friends, as in people you are going to share ideas about schoolwork and even life in general. So you may have someone who's doing matric in Mpumalanga, for example. Those people can be a quick access to the paper that was written. For example, term 1, term 2 exams, right? You can have those. And you do the same as well. You provide them yours. That way, everybody gets to be in shape at the same time. Okay, stop sharing unnecessary things like a video of who did what, where, and it's trending, it's ridiculous. Those things don't matter, guys. If you don't pay attention to these nonsenses, they will stop happening, believe me. But the more you trend these, and you watch these, you comment on these, you talk about these things, you are actually promoting these things to keep escalating. And that's not what we need, okay? Right, let's do this last one, guys. Into apha. Masike siyikrwele nje sibone. Yho, ndiyonqena nokuqhubeka, but I want to do it for you guys. I'll leave that page for some notes. I'm a bit tired, and the sad part is that I'm on duty, so I'm exhausting myself right now. Okay, 3 experiments A, B, C are carried out to investigate some factors that affect the rate of a reaction. Is always the case, right? Of course, this time we're going to talk about the decomposition of hydrogen peroxide. But what is this? It's a reaction. So a balanced equation is given here. 2 moles of hydrogen peroxide decomposes to 2 moles of water and 1 mole of oxygen. Identical samples of hydrogen peroxide are used in each experiment. See, that is what is important. Identical meaning mass, basically. And perhaps a state of division, I suppose. Maybe, we don't know, but we can talk about mass without a shadow of doubt. But other things like state of division, be very careful. Right, so it says the conditions used in each experiment are summarized in the table below, right? We've got A, B, C. And we see the temperature is the same for the first 2, but it's different for the other one. Now, this is without a catalyst for 1. The 2 is with a catalyst. And then 3, just a higher temperature without a catalyst. Now, guys, if you look at this, if you look at this decomposition, what do you think? Is it a spontaneous reaction or is it a non-spontaneous reaction? This is very important. So look at at A. If you look at A, you will see that this is happening at room temperature, as we say in chemistry, 25 degrees Celsius, which is 298 kelvins, without a catalyst. And this reaction occurred. So what does it mean? Spontaneous. So sometimes there may be indication on extra pieces of information because it's not so easy to look at that and essentially see, what can I say, and essentially see that this is spontaneous. But again, if you know the table of electrode potentials, you would know that that reaction actually features there. So whatever you see there stands a chance of being spontaneous alone, because that's what we call standard reduction potentials. Once we say standard, we're saying STP. Essentially, this is what would occur anyway at room temperature, I suppose. But I could be wrong to say that, but that's essentially what is happening there. Now, the other issue is to say, okay, let's look at this thing now. What is happening here? If we look at this, look at the oxygen here. We know that oxygen has a 2 minus. But now when we double this, it becomes a 4 minus, right? Hydrogen has a 1 plus, right? And as we can see there, we are giving it a 4 plus so that it matches the 4 minus as a result. So that is quite a stable compound. But now we continue, we'll see that the hydrogen remains a 4 plus in essence. But if we look at that oxygen, you'll see that this oxygen was a 2 minus there. This is still a 2 minus, okay? Right. Let me see again. What am I saying? That is 2 minus, right? Times 2. Because of the subscript, it's a 4 minus. Times this, it becomes an 8 minus. So that's an 8 minus there. Now, in this instance, we see that this is a 2 minus right now. Because, of course, with the 2, it becomes 4 minus. And then the hydrogens become a 4 plus. So in a way, that's fine. But we see that this oxygen becomes 0. Okay, So in essence, if we look at that oxygen, we can see there that there is an increase in the oxidation number. Why? Because the negative ones in this case, we regard them as small. 0 is bigger than the negative. So we essentially see that effectively the oxygen is undergoing an increase in, an increase in the oxidation number. So it is undergoing oxidation. Okay. Where the hydrogens, as we see them, they are pretty much spectator ions here. There's nothing changing. So it's like the oxidation of oxygen. So would we say now this is a redox reaction? Not necessarily. But we do see this there. So unless I'm not analyzing this correctly, but that's just what I see. So in essence, the oxygen is increasing in the oxidation state. So this is just the oxidation half reaction, so to speak. Again, you can consult those tables of standard electrode potential. Let me just check this one I have next to me. So remember, guys, this is a discussion. So unfortunately, it's not a quick answer video. It's a discussion so that there is some perspective to what this is going on. So hydrogen peroxide, where are you? Show your face. As we can see there, but this one in the standard electrode potentials, it's actually shown rather differently. So it's acidified, and of course we form water. No, it's not the one. Where is the one? Where is the one, guys? Yes, there is the one. So we've got H2O2 with a plus 0.68, reduction potential there. When it undergoes oxidation, we can see that it's oxygen that it releases. Of course, this one is acidified to some extent. All right, okay. It releases 2 electrons. So we know that there's going to be 2 electrons released there, 2 moles released. So essentially, that's just an oxidation half reaction. So now an oxidation half reaction, we cannot call it a redox reaction because that's not necessarily that. So I don't know what to call it. Yeah, I really don't know what to call it. But again, it's a decomposition reaction. Why am I struggling? It's a decomposition reaction, which if we were to take it into considering these, redox reactions, like I said, what you see there, guys, what you see there in the standard reduction potentials is what happens at 25 degrees Celsius, meaning it's relatively spontaneous. Those half reactions can occur without much influence, but we can see this one may need some acidification of some sort, but just to keep it on the one end because it quickly goes back. It's a reversible reaction. So just to keep it forward, we may have to, put some acid there to then keep it in one direction or more into one direction than the other. Right. But again, guys, take what I say with a pinch of salt. Remember, I am not the teacher, okay? So I am a fanatic, and a fanatic will always be imaginatory as highly as possible. So, but my imagination may not be right. But I'm just using what I have, guys. I'm analyzing what I have. Sometimes it could be a misanalysis if there's such a thing. But at the end of the day, it's worthy to be attempted because following that mistake would be a solid understanding of what happens. Because with due research into this idea and seeing again some experimentation that you may be lucky to have, then you may have a clear understanding of what this should mean or what it should be. Okay, guys, enough of the ranting. So that's the idea right there. So it's fairly spontaneous, I guess. So we can easily say that delta H here must be less than 0. Because we see that it even occurs without a catalyst at room temperature relatively. That should be fairly spontaneous. All right, so that's what we can say, guys. It says now, in which experiment, A or B, is the reaction rate higher? Of course, B. And use the collision theory to explain. Can you see here we are hit with a big one? But again, this question should already be easy to students. So it's going to be B, guys. We know that a catalyst lowers the activation energy needed for the reaction to take place. Now, this ensures, or we can say allows, this one makes more molecules Yo, come on, guys. Come on, tablet, stop messing with me. More molecules to have sufficient kinetic energy to form effective collisions. In fact, more. To form more. This allows for more molecules. Again, I think the more they captures this, because the more molecules have effective collisions, then it means we have, in essence, more effective collisions. Okay, that's just repeating myself. Okay, more molecules to have sufficient kinetic energy to form effective collisions per unit time. My writing. So if that is the case, guys, what do we get? We can say, hence, the reaction rate will be higher for B. All right, so this is very important, guys. Of course, we say the mechanism lowers the activation energy. That's a mark. More molecules will have sufficient kinetic energy and effective collisions. If there's more molecules, then there will be more effective collisions per unit time. And of course, that will translate to a higher reaction rate, and we get an extra mark for the choice. All right, easy stuff. Again, guys, apparently with these kinds of questions, there's what we call negative marking. If B is not chosen correctly, whatever argument comes here does not get marks. So it's either you get all correct or none. Okay, it's 4 or none here. Be very careful. So you don't think you're gonna botch the first one and then get the right argument. Never. 21.2 says the Maxwell-Boltzmann distribution curves X and Y for 2 of the above experiments are shown. Okay, now we can see this one has a higher peak average kinetic energy. There is somewhat lower than the average kinetic energy for curve Y, and we can see that the peak is less taller for Y. Okay, so when we shift this to the right, we know that temperature of X is less than the temperature of Y, or we can say Ty is greater than Tx. This is usually the case. Okay, So study the materials, guys, and observe what is happening. As we can see here, there was less molecules. If we were to draw the, what we call activation energy, and say perhaps it was here. Let's say our activation was here. I'm just guessing now, just doing extra stuff. So let's say that was the activation energy. Can you see the number of molecules that had sufficient kinetic energy was in that region there? But now with more, can you see we end up with more molecules having sufficient kinetic energy, and as a result the reaction rate becomes faster. Okay, so that's the idea. It says now identify curve X or Y that represents experiment C. Now if we look at experiment C has a higher temperature, so it should be Y. So this is Y. Now there's no one who's saying we need to explain, so that's it. Wow, 2 marks for just that. Great stuff. Right, so 2.1.3 says, okay, the volume of oxygen gas produced in experiment B, okay, during the first 3.6 seconds is collected in a syringe below. And we can see that volume is in centimeter cubed. And this is basically between 640 and 680. So that should be average between the two. Okay, so we can calculate how much the small little tick there represents. Since we see 160 there, that should be 80, isn't it? Because 160 divided by 2 is going to be 80. So that should be 80. So 480 plus 80 is going to give us what did I do now? 480 plus 80. It gives us 560. So we should be sitting at 560 here, centimeter cubed, right there. Okay, again, the other way to do this, you can take the average of the two numbers on either side of that tick. So we can say 480 plus 640, and then we divide this by 2. It gives us 560. So there's many ways of killing a cat. Please kill it. So we know the volume is 560 centimeter cubed. Very important. Okay, so we are told to write down the volume of the oxygen gas collected in the syringe. I mean, come on, guys. You cannot give that one, because it's not like we are calculating it, we are writing it down. So this is 560 centimeter cubed. At least you know how it's done. Of course, you would not have had this answer in the exam, so you would have to cough it up, or you swallow it up. Now, essentially, A1, 21.3, kwenzeka ntoni apha? 10 ngosend ku 21.3. Did I skip questions? Oh yeah, okay. Bad execution here. So this is 21, not 2.1. Whew. Yeah, guys, the numbering can be quite a nightmare. Please pay attention. So this is 21.3.1. We can say 560 centimeter cubed. We get our 2 marks. However, we did it 21.3.2. Be careful, guys. When somebody says show, you can't just write the answer, okay? But when the question says write down, you can, okay? Now this one says calculate the mass of water that was produced during the first 3.6 seconds. Take the molar gas volume to be 24 centimeter cubed per mole, okay, at 25 degrees Celsius. And we can see they were given a range of answers because it will depend on our accuracy here. Okay, so we want the mass of water. So here's the equation again. We've got 2 moles of hydrogen peroxide. Right, which decomposes to 2 moles of water plus oxygen gas. Right, so what are we going to say? We know and understand that we used the mass of oxygen. So the mass of oxygen and water is a 1:2 kind of a relationship. We don't write the 1, okay? So 1:2. So this means for every 1 mole of oxygen produced, there is 2 moles of water that was produced as well. So we know that, okay, how do I say it? Okay, you can say for every 1 mole O2 produced, there is 2 moles of H2O produced. Okay, so in essence, we can use that ratio as well. Okay, so this implies that the number of moles of water produced is going to be 2 times the number of moles of oxygen produced. Right, so this implies that the number of moles of water is going to be basically 2 into, that is going to be the volume of oxygen divided by the molar gas volume. Right, so we will say therefore the number of moles of water is 2 into the volume that we got was 560. Since this is all in centimeter cubed, we don't need to change it because a ratio is a ratio. The units will divide to 1. So what was this? 24 squared. So let's see, what is the number of moles of water then? So this is 2 into, sorry guys, 560. I'm a bit tired now. Of course, guys, I'm taking time to do this topic because I know you guys underdo it. You underdo this one, and I'm pushing you to do it well. So 0,0447 mole or moles, whatever. Right. So now that is what we do here. What we were looking for again? The mass of water. So we can say then the mass of water is going to be equal to, we can even use the formula generically, it doesn't really matter. We can say number of moles of water equals mass of water divided by the molar mass of water. So this implies 0,047 equals mass of water, which is what we want, divided by the molar mass of water. H is 1, basically times 2, plus, please don't worry about the coefficients in this calculation, we worry about the subscripts. So this is 16. Right, so we can say therefore the mass of water is going to be 0,0. Yeah, guys, I'm distracted. 0,047 into, this is 17, right? Is it 17? 18, sorry. Okay, I've kind of played with the edges too much. That should be 18. right, which is, let's see, 0,047 into 18. We get a 0, we can see here this is rounded off to 2 decimal places, so we get 0,8. Here they rounded off to 2 decimal places. Again, it's not bad, we can do 2. So this is 0, 0,8 to 2 decimal places is 85 grams. Okay, so this is within that range that we were given. Okay, 0,72 to 0,9, 0,85 is in between, so it's acceptable. Right, so this was not a bad question otherwise. So guys, here I believe the substitutions, the answer was key. The formula which answers the question, is it? Hey, there's a lot, guys. This should have been 5 marks. Okay, let's just give it. Calculating the molar mass of water was also key. But again, this says we need to not be too silly. Usually this is a 5-mark question because of the detail, but again, it's at the examiner's discretion which ones get a mark. Either way, guys, whatever formula that you've shown does not necessarily have to be the one in the memo. But if there is a formula somewhere and the formula was to be given a mark, you get a mark. It doesn't have to be a specific formula, especially when we use more than one. Right, so this is how, guys, you do these kinds of questions. As you can see, they are not really that difficult. It's just a matter of getting the job done, okay? It's just a matter of getting the job done. All right, let's see 21.4. Right, 21.4 says, the graph below, not drawn to scale, is obtained for the mass of oxygen gas produced over a period of time in experiment A. Okay, this time we're using experiment A. This is the one at room temperature without a catalyst, which was going to take longer than the others, right? Yes. So what we see there, okay, it started off being, explosively, yeah. And of course, we don't really see that much of an increase because of the release of temperature. Why? Because we actually lose that temperature to some extent because of the slowness of the reaction, it seems. So it doesn't capture that sinusoidal type of ogive-like curve, All right, great. So basically, ogive in France, when they say something is an ogive, it means it's S-shaped, it's sinusoidal. So this one is not capturing that, but it actually should, because this is not good for it to be like this. It's not good. It's actually sinusoidal. So this is a bad graph, by the way. For an exothermic reaction, of course. Now let's see. Use the information in the graph to answer the following questions. All right. So we've got two. Yeah, guys, I'm losing my focus. This is 21.4, 21.4.1. It says, write down the rate of production of oxygen gas for the interval 30 seconds to 36. As we can see, this is flat. This is when the reaction has stopped. So this is 0. So 21.4.2. So we score an easy 1 mark there. It says, will the rate of the reaction in the interval 3 seconds to 9 seconds, okay, be greater than, smaller than, or equal to the rate of the reaction at 9 to 20 seconds. So obviously from 3 to 9, guys, we can see the gradient is very steep. Whereas from 9 to 20, we will see that the gradient is much gentler. So in essence, the one at 3 to 9 is greater than at 9 to 20 seconds. So we will write greater than. Okay. I wonder if one writes greater than in small letters because we are told how to write it. What happens? Again, guys, it says you are disobeying the law. Okay, if it is written in caps, write it in caps too. All right. I don't know if it is just for emphasis purposes, but not necessarily for the student to do it that way. But remember, there's always a small catch. Sometimes when something is given in a particular way, please give it back in a similar way. All right, my tablet is losing power, and the man is losing his weight. I didn't know that this video is going to take so long. Either way, we will do it. We will do it. Right. So that's it, guys, for that. So we did it. So no explanation was necessary. So easy 1 mark. Then we've got 21.4.3. This one says the average rate of decomposition of hydrogen peroxide is essentially 2,1 times 10 to the minus 3 moles per second. Calculate the value of time t on the graph. Now remember, this time t is in relation to what? Oxygen production. So of course, the rate of decomposition of a hydrogen peroxide gives us, roughly the rate of production of oxygen. Okay. But then we need to be careful because if we look at time t has to be greater than 20 seconds. Okay, so that is very important to consider. Okay, all right. So that's somewhat a good thing. But again, guys, this is not drawn to scale, we were told. If it was, I would say, look at this distance from 30 seconds. From t to 30 seconds and the distance, between t and 20 seconds. We can see there's more space than there is here. So I would say this should not be far from the mid-20s, but certainly slightly, quite a larger margin. So you'd be expecting something like 24, 23, 24,5, somewhat. Although this is not drawn to scale, guys, but that's the impression one can make out of this. Although it could be wrong, but sometimes you look at things and you just figure out what is the possibility here, so that whatever answer you get, you are able to see when it is wrong, okay? Because it's easy to get it wrong. As you can see, the answer here is ranging from 26 to 28. So this goes with the fact that this is not drawn to scale. So this proportion is literally outrageous because it should be the one on this side. And then what is on this side should be on that side as well because of the time frames that we have. But again, in the exam, we would not have this answer staring at us like that. So we would have to think about what we see, which unfortunately, when this is the case, it's very bad for this graph to be drawn like this. Because even though it's not drawn to scale, it's clear that this interval should have been here. And this interval should have been on this side. So this is one of those little things that I wonder if the creators of these questions ever think about. Because as much as something is not necessarily drawn to scale, it still has to make sense. Because once I get an answer, guys, that is above 25, I would start to question it. Because I'd be like, but according to the graph, this is suggesting that I'm not midway between 20 and 30. I'm somewhat before midway, you see. Now when I get an answer like 26, I'd be like, hold on, what the hell? That doesn't make sense. So I wonder if people ever consider these issues when they create these questions. But again, it just shows, man, that these things do not get discussed. After someone has just produced a paper, whoever receives it just passes it without looking. This is another negative effect of some checklists that are carelessly constructed. Because as much as you can tick all the boxes on the checklist, I think it's still okay to then do a double check. A double check is to go through the paper as the person, doing the quality assurance. You should sit down and actually answer these questions. Consider things of time, that were you able to answer this question paper within reasonable time, using as basic a knowledge as a matriculant would, to gauge whether matriculants would reach a particular solution to a particular question, depending on its level of difficulty, of course. Is it within reach for a matriculant? Then we look at some specific issues like this now. I mean, if I'm looking at this graph, it's giving the wrong impression. So what happens to a student who will calculate and get the 26 and then scrap it because they feel, okay, this doesn't make sense, because the time intervals I'm given there are suggesting otherwise, you see. So that thing of saying not drawn to scale is not good enough shield for this kind of nonsense that we see here. Okay, I'm being brutal and harsh. I shouldn't be. Should be more accommodating. I apologize. Okay. It says the average decomposition of hydrogen peroxide. Remember, given the hydrogen peroxide, but here the curve we have is the production of oxygen. So that means we need to look at the relationship, the molar relationship. As you saw what we did above, it kind of underlies what we should do here. Although I did this question before, I kind of botched the answer to some extent. But again, if you look at my answer though, it made sense in the framework of the time intervals that we are given, because I was basing most of the sense in looking at those time intervals. The answer I got was around 21 or so. Yeah, I think I got 21 some change, which made sense, by the way. Because if you look at the time intervals, it would make sense in the given scenario. But then you can see everything was switched. So it means we needed to use something else. So now since we have known how to do it better, then we're going to do it better. Right. So let's get to the business, folks. What are we going to do? We write our equation. 2 moles of hydrogen peroxide line decomposes to just 2 moles of water plus 1 mole of oxygen. At this stage, I'm not interested in the states of division, or should we say, whatever that is, the phases in which those substances are. Okay, maybe let's just not be too relaxed. We need to be particular. I said precision, so we need to do it. It's a pity this was not a good design of that graph. Kind of misled, because the range of answers is saying otherwise, which is ridiculous. All right. Okay, all right. So guys, we need the time. All right, okay. So if we look at this business right here, I mean, there are many ways of doing this, and the way I did it made sense, and it kind of made sense in the it made sense according to the graph, which I would accept my answer, then I would accept this one, purely on technical basis, I guess, rather than to say in general. No. Okay, so how are we going to do this, guys? So, well, we can look at the rate of production of oxygen by using the molar ratio. We can see that hydrogen peroxide is 2 moles at a time interval, whereas we are producing just 1 mole of oxygen. So we can use the molar ratio to find the average rate of oxygen production. And from the rate of oxygen, we can then calculate the time. Okay, so that can help us to do the time. So let's do it. So we can simply say, okay, we can see that essentially 2 moles of H2O2 basically produces 1 mole of oxygen. So this implies that the rate of production of oxygen is going to be 2 times the, it's going to be half. It's going to be half the rate of production of use of hydrogen peroxide. Okay. So what are we doing now? We will say this implies that the reaction rate of oxygen production is going to be the half of the one that we were given. So this is 2,1 times 10 to the minus 3. Therefore, the reaction rate of our oxygen production is going to be, okay, so we've got 0,5 into 2,1 times 10 to the minus 3. So what we get is 1,05, times 10 to the minus 3. Mole per decimeter, mole per second, sorry. Okay, right, so what are we going to do now? We know that that's the average rate of production of essentially oxygen. Now we can just look at the time interval, because this is at the end. This is when the reaction stops. As you can see, at this time interval, this is when the graph plateaus. So meaning the reaction has stopped. The reaction rate is 0 there. So we can look at essentially, the change here. We can say, of course, then we understand that the reaction rate in general, this is the product now, it's going to be the change in mass, for example, because here we are given mass, but again this is moles. Okay, this is going to be the change in number of moles per unit time. So we go on and substitute. So this one is going to be 1,05 times 10 to the minus 3 equals, we can see that the change in number of moles here is going to trick us a bit, guys, because we need to think about how much did we start with of the hydrogen peroxide. Were we told? We were not told. We were not told. Oh, I sorry guys, I forgot. We're using oxygen. We are using oxygen. So the number of moles of oxygen here is going to be the volume obtained, which is 0,9. Okay. In fact, not necessarily the volume this time. We can use this one, the mass. It's going to be 0,9 divided by the molar mass. So we know that we're going to have basically 0,9 divided by the molar mass of oxygen is 16 by 2. That's 32. Okay. Remember, that would be the change because the product started from 0 to this amount. So that's the change. So this we divide by the time interval, which is basically just t minus 0. So that's just t. Okay. You can say therefore our t is going to be what we have here, 0,9 divided by 32, all divided by 1,05 times 10 to the minus 3. Let's see if we're going to get an answer within the range we are given. So we've got here a 0,9 divided by 32, and this is all to be divided by 1,05 0.05 times 10 to the minus 3. Okay, so what do I get here? The time I get indeed is somewhere there. So this is 26.79 seconds, because this is seconds. Okay, so it's a bit of a technical situation, to be honest, because we do get an answer within that range. But again, you see, it's not quite representative of what we were given. And the manner in which I did it the last time, you will see that if you go and check the chemistry paper for November 2022, you will see I did it differently. And the answer makes sense for the given diagram. So essentially, you can argue about it all you want, but at the end of the day, it's all about technical issues. And if we ignore those, then we don't know what we are doing. But again here, because we are given a clear indication of what's cooking, we had to go about it, of course, in the manner that would kind of drive us there. But even if it didn't, I guess we should be able to accept what happened. Anyway, guys, stick with this technique. Perhaps stay away from that other technique. But at the end of the day, you never know when there is a catch in the calculation. Because when something is misrepresented, then the catch becomes almost impossible to defeat. Because even you know the right thing, sometimes you get caught in between that technique I showed and this technique right here. Either way, guys, you know what to do now. So for me, when you're caught in between those two, any that you present for me should be okay. But again, it will take fighting for that to be accepted, because yeah, some people are complacent. They'll just take the answer for whatever it's regarded as, and then not see the technique that the student used and not see the point to give a mark. Of course, you may not get full marks if you don't get to the right answer. But again, people need to look at the question itself. Did it give the indication, though, that such an answer was incorrect, and for a student to notice that? If not, then we should accept the full answer for full marks. You know. So anyway, guys, this is the story right here. Quite an interesting question otherwise. Spare that it was poorly constructed from the graph standpoint. Anyway, enough of the rants. Let's see what are we gonna do here. This business right here is key, guys. And that business over there is key. Then using our formula, nicely calculating this dude and the answer. 1, 2, 3, 4, 5. And we've got all our marks there. Nice and easy, guys. So this would end our work on rates of reaction by me, your tutor, if you regard me as such. But I'm no more than just a comment. What do you call? Commentary. Is it commentary? Yeah. It's just a commentary that I'm passing here. I wouldn't regard what I'm doing as teaching. At the same time, it can be useful if used correctly, of course, but be very careful of what you get from me. It may clash with how things are to be done. So take it with some caution there. That I might be wrong, maybe irrelevant, but at the same time, I'm sharing an idea. If you use it well, you might get somewhere. Anyway, guys, this is just to demystify the first beast of chemistry, or the first danger. Because of the trio, this is a much approachable danger. So you can call it a dog in a home. But now we're going to get to the tiger and the lion. These two are very difficult to separate in terms of strength. But yeah, yingwe nengonyama, qhumuthule, akho winner, akho loser, kuyafiwa. All right, let's get to the lion and the tiger. Okay, guys, so let's continue. So I've had a bit of a distraction work-wise. So So let's look at some notes again. So chemical equilibrium, folks, is an important topic. So this is when we have products that are converted back into reactants. This is when we talk about a reversible reaction. So this is a question that is present in the exams most times. So we need to talk about what is a reversible chemical reaction. And of course, we need to talk about what is a closed system in chemistry. It can come. So students need to know that it is a system that only exchanges energy, but not matter. And I think we did speak about this in the physics video that I did. So I hope you guys sometimes use these together, because some concepts actually do come together. And of course, if you look at a chemical bond, it's actually the force between the two molecules, or should we say the two atoms, or any number of atoms that make up a molecule. So in essence, those are electrostatic forces. So Coulomb's law actually is still there. It's forces, Newton's laws. So folks, don't think chemistry is a different subject. Okay. Right. So of course, that is the requirement for any system to undergo a chemical equilibrium. It has to be a reversible reaction, and we must have a closed system. Again, watch the videos I have produced for chemistry, and you will see that narrative coming up nicely. Okay, so we can talk about a dynamic equilibrium. This is when the rate of the forward reaction equals the rate of the reverse reaction, such that the amount of reactants and products remains constant. Not equal, but constant. Please remember that part. Okay, we can say conserved if we want to. All right, so again, folks, we need to think of factors that can affect the equilibrium position, right? So a catalyst can do it, concentration can do it, temperature can do it, and then pressure when gases are involved. Of course, we can only think of a temperature. An endothermic reaction is favored by an increase in temperature, whereas an exothermic is favored by a decrease in temperature. This is all the stuff that is based on Le Chatelier's principle. And again, we need to be able to state it without flinching, okay? Please. Of course, guys, there's not a lot for me to say. Of course, look at the terms and definitions, because this is examinable and it often comes. So, so when we talk about, say, for example, an open system, what is it? What is a closed system? What is a reversible reaction? Okay, and then what is a chemical equilibrium? Sometimes you can say dynamic equilibrium. So factors that influence the equilibrium position, and of course, Le Chatelier's principle. Of course, guys, read through these, and most important is to know how to formulate the Kc equation, okay, or the expression. What is to be included and what is not to be included. So solids are often not included because the concentration is taken to be 1. It's fairly constant, okay? Right, of course, guys, this highlights again on how to solve problems using Kc, and there are a few examples that are provided here to demonstrate that. So I would expect students to read through for themselves. Now, another key issue is to learn how to interpret graphs in chemical equilibrium. Of course, it's much easier when we've got the rate of the reaction on the y-axis, because we know the one that starts off at a given value would be the forward reaction. Don't be fooled by the dashed line and say the one with the dashed line is the reverse. No, it can be that one that is dashed, just to check if a student understands this. So in essence, the one that starts at 0 is usually the reverse, because it only picks up as the forward reaction slows down, okay? Right, we need to get that. But with the concentration graph, it's very difficult to say for sure, because I can tell you this is the forward reaction. Would you disagree? The formation of products is the forward reaction. Also, the use up of reactants is the forward reaction. So this one gets a bit ambiguous in a way. But the very strong point, of course, I see that those who made this note said this is the reverse reaction, and that's not exactly true. But it could indicate the presence of a reverse reaction, because the more products we start forming, automatically we know there's going to be a reverse reaction taking place. But this is not truly the reverse reaction, but it's an indicator that it starts to be present. But these two graphs, in essence, they speak strongly about the forward reaction, in my opinion. Of course, I could be wrong, folks, but again, a concentration time graph for chemical equilibrium makes it a little bit difficult, especially when we are looking at the start until we reach equilibrium. But if we can provide a disturbance here, and from that disturbance, okay, just a moment, guys. All right, folks, so what I'm saying is if a disturbance is introduced, it can give us an indication as to which reaction got favored. But we cannot say a particular... Oh, God. All right, so, yeah, my family is also trying to interrupt me as well. So apologies for that, guys, but I'll talk to them later because I want to finish this before I get very busy because I'm on duty technically, so... Right, folks, so what I'm saying is when there is a disturbance that we can see, it may give us an indication of as to which reaction got favored, but we cannot say specifically a specific line represents a specific reaction in this case, because it could be quite a disaster to say that. All right, because we can say this is the forward reaction, but when we see an increase, for example, like this, what does that mean? We favored the formation of reactants, isn't it? And that is the reverse reaction, but you see, within the very same framework. So this is kind of, ambiguous in a way. So be very careful. Rather look at the influence as to what it indicates rather than to say this is, because you cannot say that. It's not really possible. Anyway, enough of the chit chat over that. Again, believe what you will. At times, no matter how much you try to give people, the essence of something, they still will fight it sometimes. Sometimes they will just not see it. Sometimes they will just not accept it, irrespective of knowing and seeing what is going on. Anyway, my job is not to convince you guys, but it's just to enhance your awareness in these situations. Okay, look at the graphs again, guys. You see when there's a disturbance, you see what a catalyst will do. Does not discriminate the forward versus the reverse. It increases them the same way, in essence. That's the catalyst. It's non-discriminatory. But temperature and pressure temperature may increase, but it will favor a particular reaction over the other, which plays catch up. With, again, a decrease in temperature, it's sort of like both dropping, but a certain one favored over the other. So temperature is discriminatory in a way. We look at concentration. Again, the concentration is discriminatory as well. It may favor a particular reaction over the other. But of note, I forgot to mention about temperature. Temperature can also change the Kc. It's only a change in temperature that can change Kc. I think that's something that needs to be remembered. So temperature change can change the Kc value. That's the only one. The rest do not. Perhaps that's just an important note to consider there. Okay, guys, please learn how to read and interpret these graphs and be able to tell the types of disturbances that have occurred, and perhaps use Le Chatelier's principle to explain this. So please read through this and make sure you understand. As I said, this is going to be available. This is going to be available for you guys to have a look at. So let's take down this question 1. So I'm highlighting these questions that we have done, guys, so that when you look at the memo that I'm going to provide, you will know exactly which questions in this document I have discussed. Okay. Right, so question 1 on chemical equilibrium here in this document. So we've got some issues here, you see. Of course, this is the nitrogen dioxide gas changing into the dinitrogen tetraoxide gas, which, by the way, I've had the privilege of doing this in the school laboratory when I was you. So, yeah, this one I never forget. Okay, so again, guys, you see, we are told to discuss or at least explain what is chemical equilibrium. Now, this one is a bit technical in a way because there's two possibilities here. We can say it's a chemical equilibrium state whereby the concentrations of reactants and those of the products remain constant. Or you can easily say it is a chemical reaction whereby the rate of the forward reaction is equal to the rate of the reverse reaction. These two things mean one and the same thing, okay? So you pick what you can say. There's no one who's going to tell you, no, choose the one over the other. They mean the same thing. So what are you trying to say? Because if they remain constant, automatically we are suggesting that the rates of the forward and the reverse reactions are equal. And when that is the case, we're also suggesting that essentially the concentrations or the amounts of products and reactants somewhat remain constant. So in essence, there cannot be an argument that wins over the two definitions. So one of my students was like, yeah, in the exam guidelines, it has to be about the rate of the forward and the reverse reaction, but the essence of it is what matters as well. So if something explains the science, please guys accept it. But again, I'm not saying don't write what the exam guidelines say, although that kind of behavior for me is unacceptable to be enforced that way. It should be a mere suggestion because that's the least you should do. But that's not the only thing you should say, okay? If you can say the same thing in a different light, so why not? Anyway, whatever, guys. So let's have a look here. What is chemical equilibrium? We can say it's a chemical reaction. Or we can say chemical equilibrium, it's when a chemical reaction reaches a state where by the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, you can even add such that the concentrations of the reactants and those of the products remain constant. You can make it all complete such that the concentrations, or we can just say the amounts rather, such that the amount of the reactants and products remain constant. Okay, learn to say things completely, because you may be asking a question, but why? Why must the reverse be equal to the forward reaction? So what is the implication? You don't want a follow-up question when you say a definition. You want to make it complete and clearly understood. So yeah. So I'd say 1 mark for the first part, 1 mark for the second part, but again, guys, you can stop it right there. It's not a big deal. Okay, easy 2 marks otherwise. So 1.2 says, at equilibrium, the concentration of, did we read? We did not, goodness. We're told a certain amount of nitrogen dioxide gas, you see a certain amount, it's not known, is sealed in a gas syringe at 25 degrees Celsius, okay? When equilibrium is reached, okay, you can clearly see this is a spontaneous reaction. Why? Because it happens at 25 degrees Celsius, okay? So when equilibrium is reached, the volume occupied by the reaction mixture in the gas syringe is, again, 80 centimeter cubed. The balanced chemical equation for the reaction taking place is 2 moles of nitrogen dioxide gas, of course, converting to 1 mole of dinitrogen tetroxide gas. And we can see this also gives it away. Can you see we are applying, issues that we just did in the previous chapter. So it is quite a useful thing to remember. But even that 25 degrees Celsius already was indicating this is what happens without an influence from the outside. Okay. Right, so let's look at 1.2. Now we are told the concentration of nitrogen dioxide gas is 2 moles per decimeter cubed at equilibrium. The equilibrium constant for the reaction is 171 at that temperature. Now we need to find the number of moles initially for the nitrogen dioxide gas that was placed in the syringe. And then, of course, an answer here is suggested so that we can see what we are working towards. So this is the KC calculation, basically. All right, so we've got 2 moles of nitrogen dioxide gas. Which automatically converts to some proportion of dinitrogen tetroxide gas. All right, okay, all right. Now, we will start here and say, okay, at the start. Okay, one of my students said I should write the rice table and say it's a rice table. Okay, it's the rice table, guys. Of course, this is number of moles. We know that small letter n in chemistry represents number of moles. We don't need to say it in words per se. Of course, here we can think about the change, or we can say used and produced, if you will, but I think change captures it nicely. So what has changed? This is what actually takes part in the reaction. And then equilibrium, number of moles, is actually what is left over once the reaction has taken place and reached equilibrium. Then we can talk about the equilibrium concentration. Now, once we put square brackets, folks, we already mean molar concentrations, okay? This is in moles per decimeter cubed. There is no need to write the full units. Just the symbol itself is enough, okay? Right, so we know that we didn't know what we started with in terms of number of moles. So we can say, well, let that be X, and then there would be nothing of the dinitrogen tetroxide gas. Right, so at equilibrium, we are now told that the concentration of nitrogen dioxide gas is 0.2 mole. So we are given this one, 0.2. And of course, we can then calculate the number of moles at equilibrium here, because we know that concentration is basically number of moles over volume. So we know that basically 0.2 is equal to the number of moles divided by the volume. We're given that the volume is 80 centimeter cubed, so that's going to be 0.08. When we divide that by 1,000, it has to be a molar volume, should we say decimeter cubed, yeah. Because this is a molar concentration, so this is going to be 0.08, okay? Which gives us that the number of moles is the product of the two. So 0.08 times 0.2 gives us a 0,016 moles. I'm just showing this so that you guys can see it. In fact, I can stretch this a bit so that it does not affect my writings here. Let's give it some space. Okay, right. So after we've done this, so this means, guys, the change that happened here is going to be x minus what is left over, isn't it? So this is basically going to be x minus 0,016. That would be the change. And of course, since we see that 2 moles produces 1, so we just have this. So when we have this, we know that on this side we're going to have, perhaps let's just write it like this. It's going to be 0,5 into x minus 0,016. We can leave it like that. It's not a big deal. So that's what we needed. And of course, at equilibrium, we're going to have the same because we started with nothing. So if this is what we produced, it's essentially what we will have. And of course, here we will have 0,5 into x minus 0,016. We then divide it by the volume, which is 0,08, to get the concentration. Very important, but the other one was already given, so we don't need to show the calculation for it. All right, so now our rise table is complete, so we can go to the Kc and say Kc is going to be N2O4. Of course, this is to the exponent 1, so we don't show this. NO2, so this is going to be squared because there is a coefficient of 2. So let's go on. So we know that Kc was given as 171 equals, what's the concentration there? This is basically 0,5 into x minus 0,016, all divided by 0,08. Of course, at this stage, I'm just going to use that division like that because it's going to mess up my expression. So this is divided by the concentration here of 0,2 squared. As long as the mathematical expression is right, it doesn't have to be exactly like this when it doesn't allow. Okay, I just hate complexities. Okay, guys, so let's deal with the right-hand side first. So this is 171 over 1. It's a fraction. Now we're going to essentially flip this. This means we're going to multiply this flipped. So this becomes 0,5 into x minus 0,016 divided by 0,08 times 0,2 squared. Much better, isn't it? Now, when we cross multiply, what we will get is essentially 0,5 x minus, let's multiply this one, 0,16 times 0,5 becomes 0,08. So this is 0,008. Okay, great stuff. Equal to, we then multiply the other two, so 0,08 into 0,2 squared into 171. I'm moving fast, guys, so you don't have to. So I'm getting 0,5472. Great, so we solve for x. We know that x is going to be 0,5472 minus, in fact, plus 0,008, all divided by 0,5. Therefore, x is, in fact, yeah, x was a means to an end, okay, but we can solve for x for now. So plus 0,008 divided by 0,5. So what I'm getting here is 1,11 moles. And exactly the answer that we were supposed to find. We can say, therefore, remember we're not solving for x per se, we are applying maths here for a placeholder, but what are we solving for is the concentration, the number of moles. So we can say N of NO2 initially is 1,11 moles. We need to answer the question. So as we can see, guys, it's a matter of just knowing how to get the table right. And the trick is within the table, usually, because the rest is just algebraic gymnastics that you already know. Okay, guys, so essentially, we can say, fine, determining the number of moles is quite a skill, right? And then to work out the change, as well as to work out that number of moles there, and the concentration, that's the first 4 marks, okay? KC expression, good. And then substitutions, also good. The gymnastics, folks, are the gymnastics, are they not? Okay, let's see, how many marks is this? 1, 2, 3, 4, 5, 6, 7. Okay, where is the 8th mark? Maybe we can say the technique of putting X there. That should be the 8th mark. Otherwise, it is what it is, guys. It is what it is. Okay, everybody's looking for me. I will look for them later. They must just chill. Alright, so guys, this is the big bad boy, if not a girl. But girls are never bad, so we can say it's a big old boy. Big bad boy. Triple B. Girls are never bad, so then they're never big, right? Yeah, girls are never big and they're never bad. So yeah. All right, so let's not waste time, guys, because I'm gonna lose it if I do so. So 1.3 says, okay, the diagram shows the reaction mixture in the gas syringe after equilibrium is established. Okay, this is cool. We see what we see there. Now the pressure is now increased by decreasing the volume of the gas. We did this, guys. It's so beautiful. At constant temperature, as illustrated in the diagram, the diagram below. And we can see that when we increase pressure, this gas becomes darker. Why? Why? Well, so let me see. Hey, wait a minute. This is not quite true for what we normally do, eh? You see, that one was light brownish, but this one became darker. I think there's a mistake here. We should be having a mistake, unless that equation is not well balanced. I'm starting to think so. Is it well balanced? There's 2 nitrogens, 4 oxygens. Yeah, it's balanced. But now this is not good. It's not right. It doesn't talk science, eh? Because remember, an increase in pressure is going to favor the side with the least number of moles. That would be the N2O4. It should become light brown, not dark brown. So this is not good, eh? Not good. So now this fails the question. So it says, immediately after releasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. hey, immediately after releasing the pressure. Hey guys, what I'm but this is a misrepresentation. This is wrong. It should be light brown, hey? It should be light brown, not dark brown. But again, we are told that this happened when the plunger was released. But can you see here, this is the beginning of the situation before the pressure was applied, you see. This one says it's light brown. No, that should be dark brown. Then when we put pressure, it should become light brown. Okay, so I'm not sure what the examiners were trying to do here. They got themselves confused. Or the person who designed this didn't get the idea. And again, these are some of the issues I don't like about these questions. All right, anyway, we've got 31.3.1. It says, okay, immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. Increasing pressure, favoring the most number of moles. I've never had such a thing. This is so wrong, okay? Give a reason for this observation. Oh, God. Oh, God. How can we give a reason for that? This is not possible to answer because it's incorrect. You know, it's incorrect. It doesn't speak the science. And if I remember well, but again, guys, that was how many years ago? 2005. 20 years ago. What did I say, guys? When we put pressure, the thing became light brown. When we released the pressure, it became dark brown because we collected it dark already under less pressure. But as we put pressure, it became light brown. You know. So this one doesn't make sense now, guys. So unfortunately, that question is bad. It's botched. Okay, it says the color of the reaction mixture in the gas syringe now appears lighter than the initial color. Okay, so this one, guys, I accept. You know, after a new equilibrium is established as illustrated below. Okay. Yeah, anyway, guys, there's a few things that we need to think about. Now I'm starting to see that I'm probably going crazy myself. Okay, let's just think about this for a second, because it's easy to get the examiners wrong when they're actually right, you know. It's easy to get them wrong. But for me, this is brownish, okay, that's fine. As you can see, the tinge here and the tinge there is different. So, okay, let's look at it nicely now and not rush. So, at the beginning, when we apply pressure, what happens? We increase the concentrations of both. That's why we are told immediately. So, I'm the one who's missing the point, okay? So, immediately, yes, it will become darker, but as you keep it there, then we know we're going to favor the forward reaction, and therefore the color becomes like this. This is after a while. Okay, now I accept. I was wrong. So you see, it takes a moment sometimes to answer these big bad boys, you know. They make you think you are right and you are wrong. Okay, so you need to think again sometimes. All right, as we think again, okay, we are told to give a reason for this observation. It's because initially, you need to say that initially, the concentration of NO2 will increase as well as that of N2O4. We know this one is a colorless gas, right? Compared to the NO2, which is brown. And so if we increase the concentration, the NO2, but I think the NO2 is more responsible for that. Initially, the concentration of the NO2 will increase as well as that for the NO2. Of course, NO2 is brown, so we can move this just to give that little piece. It's brown, and then this one is colorless. But of course, the combination of two will give a light brown color rather than a completely colorless color. Although this one is almost colorless, but there will always be that tinge of brown vapors there. Okay, all right. So we know that initially, what is important is the initial part. The concentration of Danton will increase with increased pressure. Maybe let's put it that way. Will increase with increased pressure. As well as that of N2O4, which is colorless. Because it's not left behind, but if it is colorless, it kind of does not affect that one in terms of the color. Initially, that's why I missed this part. All right, so please guys I said precision here is key. If you are not precise, you can easily complain, unduly so. All right, let's look at this one. It says now, okay, the color of the reaction mixture in the gas syringe now appears lighter than the initial color. Remember, this is when we have reached the new equilibrium, meaning we have favored the forward reaction and then the other one had to play catch up. Okay, now we need to use Le Chatelier's principle to explain the color change observed in the gas syringe. Again, this is a popular question, guys, that students need to know and to answer well. Okay, so we know that an increase in pressure will initially increase the concentrations of the two, but the forward reaction will be favored as it has the least number of moles. We need to say that. So initially, the concentrations of NO2 and N2O4 will increase with increased pressure. Although the forward reaction, will be more favored since it has the least number of moles. Okay, so what can we say now? We can say, therefore, the color of the reaction mixture will be lighter as more N2O4 is formed. Of course, guys, we captured Le Chatelier's principle here already by saying the forward reaction will be favored since it has the least number of moles. We can say pressure, an increase in pressure favors the reaction with the least number of moles. Perhaps we should say that to clearly state Le Chatelier's principle. We can make this the first bullet perhaps, and then the second bullet here, and then the final bullet here when we make the conclusion. We can stop this one there and then say, okay, yeah, although the forward reaction will be favored since it has more number of moles. Again, we have already stated the disturbance, and we've stated what Le Chatelier is going to do, right? Least number of moles is our key here. And of course the reaction mixture will be because of more N2O4 than the NO2. Okay, so we get our 3 marks by stating the disturbance, stating how the reaction is going to start to move, of course by being favored, and of course the conclusion that makes some sense. Of course, if we give a valid argument, we get our marks, guys. Of course, there are many ways of phrasing it depending on how we feel and how we are at the time we answer that question. So yeah, guys, I'm losing my focus. Anyway, let's continue. The temperature of the reaction mixture of the gas syringe is now increased and a new equilibrium is established. How will each of the following be affected? Okay, 1.4.1. The color of the reaction mixture. Write down darker, lighter remains the same. Now we know that the forward reaction is exothermic. That means the reverse reaction is endothermic. Now as we can see, if we increase temperature, we will favor the reverse reaction. So we know that when we put it in a hot water bath, this thing becomes darker. All right, good. Because it does this in 2 ways. The kinetic energy of the particles increases, they collide with the walls the most, then the pressure rises. Yeah. It's too complex if we go that route. Let's just understand that temperature will favor the reverse reaction, and that is the formation of NO2. So it will become darker. Okay, easy 1 mark. Sometimes we may have to explain this, but we need to know that, of course, increasing temperature will favor the endothermic reaction. The reverse reaction is endothermic, and so the color will become darker. That's using Le Chatelier's principle. Now, the value of the equilibrium constant, will it increase, decrease, or remain the same? Remember, the Kc depends on the products, because Kc is the concentration of products divided by the concentrations of reactants. Now we saw that we are forming the reactants, so we are increasing the concentration of the reactants. In essence, what are we doing? We are decreasing this ratio. So Kc should take a down dip. So we'll say it decreases. Okay. Right. We are losing the products while we are increasing on the reactants. So that ratio becomes smaller. So it decreases. Of course, 2 things are happening. This is decreasing while the other one is increasing. And as a result, Kc decreases. Okay, again, one may be asked to explain why. Be prepared to do so, because a question like this can come, and as it comes, one needs to be able to answer. But these questions are common, guys. It's always there. Use Le Chatelier's principle to explain the observation, whether in 1.4 or in 1.3 or even here. This can be asked, okay? So the interpretation using Le Chatelier's principle is really key in these topics, guys. So we need to be the masters of our fate here. rather than the fate mastering us. Yeah, let's go on, take one last example and let it be. Okay guys, let's take another example. I'm gonna highlight it so that you guys know which one it is, and then you can go on and practice it. Yeah, doch, it likes to do this to me. I don't know why. It always does it. So I'm marking this so that you guys can see them when you download this document. I think this question is good to look at. That was June 2018. Maybe we can take one more since we are trying to establish something here. Right, so it says the equation below represents a hypothetical reaction that reaches equilibrium in a closed container. Right, after 2 minutes at room temperature, and we can see that this is 2 minutes and these graphs are constant, meaning they have reached equilibrium. Right. So at room temperature, again, this is to suggest this is a spontaneous reaction. And if it is a spontaneous reaction, what is delta H here? Is less than 0. It's always for the forward reaction unless otherwise stated. So we saw that that piece already gave us the other piece. All right, guys, so can you see, once you get the hang of this, it becomes easier to handle. Okay, now the letters X, Y, and Z represent the number of moles in the balanced equation. So this is basically the molar ratio. Okay, not necessarily the number of moles, but the molar ratio. Okay, cool. Now the graph shows the change in the number of moles of reactants and products versus time during the reaction. Again comes a question, define a dynamic equilibrium. Of course, once we say dynamic, we are talking about the rates of the reaction. I mean, what you call, the reaction rates of the forward and the reverse. So, very important stuff. Okay, let's leave some space for some extra notes there. If you get a hold of this document. So, question 12. So again, guys, we need to do the exercise. As boring as it is, we just have to dynamic equilibrium. It is the state in a chemical reaction whereby the rate of the forward reaction is equal to the rate of the reverse reaction in a closed system, because this is only possible in a closed system. Sometimes maybe an extra, sometimes maybe, but I think the anchor is the rate of the forward reaction equaling that of the reverse reaction. But this is a condition for us to ever achieve equilibrium anyway. I think it's a necessary part of this definition. Of course, 2 marks for our troubles there. So 12.2. Now 12.2 says use the information in the graph and write down the value of. Okay, so how do we deal with this one? This one is key, guys. So remember, what takes part in the reaction is what matters. So meaning the changes in the amounts, because the change tells us how much these substances are reacting with each other, at what proportions, the molar ratios. So if we look for, say, for example, for A, because we see A is substance A there, is changing from, the start is 16 at time 0 to 8. So we minus 8, so this gives us 8. This is the change. Then if we look at substance B, we will see that it started at 8 and then it went down to 4. So this means we get 4 as the change. So we focus on the change, guys, nothing else, please. And then let's look at substance C. It starts at 0. And then, of course, it goes to, but you see, this is a product, so we're not subtracting, we're going to add. It goes to 12. So this is basically 12, which gives us 12. Again, this is the change. So now to deal with the ratio, we can see the reactants is A is to B, then the product is to C. So we take the changes. So this is 8 is to 4 is to 12. Then we divide by the smallest to get the simplified molar ratio, which becomes the coefficients. So 8 divided by 4, that is 2. 4 divided by 4, that's 1. 12 divided by 4, that's 3. So these are the molar ratios in there. So this is X. This is Y. And this is Z. Okay. So as you can see, guys, it's not that easy to work it out if you don't know. So please remember, this uses the change, because this is how these molecules or substances reacted at a molar proportion, so to speak. So we cannot look at the big numbers, although this one seems to match, but it's just a coincidence. What matters is to look at the change. That's what gives us the indication. All right, so we've got 12.2.1. We know that X is going to be equal to 2. Y is 1. Z is 3. And of course, we get a mark for each. Right. So we get to 12.3. Now 12.3 says, calculate the equilibrium constant for this hypothetical reaction at room temperature if the volume of the closed container is 3 decimeter cubed. So this is easy. So we know now that we've got 2 times gas A, not gas but substance A in solution, plus just 1 mole of substance B in solution, goes to give us 3 moles of substance C in solution. So we've got our initial number of moles, change, number of moles, equilibrium, number of moles, and then we look at our equilibrium concentration. That is already in moles per decimeter cubed. So at the start, we can see for A we had 16. And at the end, this is what we have at A being 8. The change is going to be the difference. For B, we started with 8. At equilibrium, we had 4. The change is 4. Okay. Then, of course, at the beginning, there shouldn't be anything for C. But now, as we change, we can see that we changed to 12 straight up. Again, we can think about it this way. 4 by 3 gives us 12, or 8 times, sorry, we can say 8 times 3 divided by 2, right? Because that's going to be 8 times 3, that's 24 divided by 2, which gives us 12. Of course, on this side we are adding, so 0 plus 12 is 12. Then the equilibrium concentration is going to be 8 divided by 3 here. This is 4 divided by 3. This is 12 divided by 3, which is equal to 4. Okay, nice. So we go on and say, fine. Kc is going to be substance C cubed divided by substance A squared times substance B to the exponent 1. We substitute. So substance C is 4 cubed divided by, this is 8 over 3 squared times 4 over 3. Therefore, our Kc will be the answer. So we've got here 4 cubed divided by 8 over 3 squared times 4 over 3. Okay, that's 27 over 4, which is 6,75. And of course, we can see that the Kc is greater than 1. What does that mean? It means this equilibrium lies slightly to the right, because it means we have more products than the reactants here. Nice and easy. Okay. So that is the story, guys, of that question. Easy, easy, easy stuff. Of course, the change here is key. The equilibrium concentrations are key. So 1, 2, 3, 4, 5, 6, 7. Yikes. Only 7 marks. Substitutions do matter here. Maybe not. The final answer does matter. So where do we stop giving the marks? I think these ones are too obvious. So let's see. 1, 2, 3, 4, 5, 6, 7. Yeah, that is it. Those ones are easy to work out. So we cannot give marks for these. And the others were literally given. So, yep. All right, so that's the 7 marks for us there. Nice and easy, guys. So again, we have to explain. Damn, I am lazy to do this, but hey, we're gonna do it anyway. Okay, so let's look at 12.4. 12.4 says at T4 minutes, we can see there is a disturbance indeed. What happened? We will see that the concentrations of the reactants started increasing, okay, while the concentration of the product started decreasing sharply. So obviously we favored the reverse reaction here. So what is likely to favor the reverse reaction? Seeing that our delta H is negative, not just delta here, goodness. Delta H. That means we favored the reverse reaction, and that means this could be a temperature change, perhaps. Right. So yeah, it could be temperature that has changed here. What else could it be? Pressure cannot affect the system. Yeah, it cannot, because these are solutions, so pressure has no play here. Yeah, because the gentle increase is starting to talk about perhaps it's talking clearly about, yeah, maybe temperature. It's most likely the culprit. Let's read. The temperature. The temperature of the system was increased to 60 degrees Celsius. Okay. Is the reverse reaction exothermic or endothermic? Explain how you arrived at your answer. Okay, we saw what this is. So now this is going to be quite interesting. Of course, we're going to say it's endothermic. Right. It's endothermic. So how will we explain this? Well, we've got a few issues. We can easily say that this is a spontaneous reaction that takes place at room temperature, meaning the forward reaction is exothermic, or delta H for the reaction is negative. that we can say. Or we can say a temperature increase favors the reverse reaction. Since the reverse reaction was favored here, therefore the reverse reaction is endothermic. So we've got options here. But let's try to use what is on the graph at least. We can say here the change in temperature resulted in the increase of amount of reactants, right? We understand that temperature, according to Le Chatelier, temperature increase favors the endothermic reaction. Okay. A temperature increase or any increase in temperature favors the endothermic reaction. This is using Le Chatelier's principle. We can say here the reverse reaction was favored. Therefore, the reverse reaction is endothermic. Okay, very nice stuff, guys. So we just say it. Okay, we get a mark for stating this, and then of course using Le Chatelier's principle, stating what we observe has happened, and of course that's the 3 marks, because essentially the conclusion is more of what we already have seen. Okay, right. Of course you can easily say there's no need to say this according to Le Chatelier per se. If no one said use Le Chatelier's principle, this approach is not a necessity. One can easily say any reaction that takes place spontaneously at room temperature is an exothermic reaction. That means the forward reaction is exothermic. If the forward reaction is exothermic, automatically the reverse is going to be endothermic. So you've got options there. Of course, we have to select an angle for the purpose of this video, but I will always highlight, what possibilities can be explored. Okay, guys, so this is a good question to get into the hang of things. Now let's look at one more question, just so that we can feel we're getting there in this topic as well. All right, guys, so there is question 17. I'm gonna mark it as well so that you guys know which one we did. That was June 2021. So we need to always do the work. Of course, guys, taking 3 examples is just to try and drive home the idea that this is the amount of work one needs to do, and as you can see, everything is just nicely processed and delivered. So please do the same, during your practice. All right, now let's look at this. It says pure hydrogen iodide gas, HI, of concentration 1 mole per decimeter cubed, is sealed in a 500 centimeter cubed container at temperature T. The reaction reaches equilibrium to the following balanced equation. So there it is. Right. Since we don't know the temperature, we cannot comment about delta H at this moment. Okay. Very important to note. Now define the term chemical equilibrium. Again, we have stated what chemical equilibrium is above. So at this stage, I'm going to skip that. So this has been stated above, okay? But don't write this stated above. Please state it. This is your job now. I cannot repeat the same thing within the same video. Ne? That would be me crazy. Okay, 17.2 says the graph below shows how the concentrations of the reactants and products vary with time during the reaction. All right. As we can see, we started somewhere at a higher concentration and we're ending up somewhere at a lower concentration. So what does that mean? This should be reactants. Okay, and of course we start with 0 and we end up at some higher value there. That should be products. Now if I ask you again, which one is the forward reaction here and which one is the reverse reaction, what would be your answer? Well, as I said, guys, the formation of products is the forward reaction, is it not? Yeah? And the use up of reactants is the forward reaction. So essentially, you can't really say. But now, if we use these as surrogates, which one would you use as a surrogate for the reverse reaction? It would be X, because the mere presence of products means there will be an existence of the reverse reaction. But this is just a surrogate marker that there is a reverse reaction, but you can't say this is the reverse reaction. I hope you understand the difference here. All right, good. Now, the only time we can talk about a particular reaction being favored is when we see a disturbance and how that disturbance affects the system. We can only comment there. Even there, we would be specifically talking about that particular segment of the graph. Not to say the entire graph represents the reverse reaction per se. Okay, please remember that. Okay, it says now in 17.2.1, which one of the curves x and y represents the changes in the concentration of the products? Of course, I like that part, the changes in the concentration. It didn't speak about the rate of change of concentration, but the changes of the concentration. Of course, that's x, okay? So that's x, okay? Then we are asked to give a reason. We can see that the products start from 0 to a particular value. So that should be the products. At the beginning, there are no products, but as time progresses, we see the graph climbing to suggest production of products. Okay, we can say initially, there is 0 products, that is T0. Not temperature, time 0. Maybe let's put it, don't do it when I'm on. Don't do it when I'm on. Let's say T0. However, hey, my writing, guys, needs prayers. However, as time progressed, more products formed, seen with the climbing of graph X. Yes, that's the best argument I can give, guys. But again, you can say whatever you will. So 1 mark for this and a valid explanation. Doesn't have to be exactly how the memo would put it. It's how you are putting it, okay? That matters. If the way you are putting it makes sense, it is accepted. If the way you are putting it doesn't make sense, it can be rejected. but it is judged on exactly how you put it rather than how somebody else puts it, okay? Remember that. Trust in your ability to express yourself in this subject. Okay, we are asked a question now. How does the rate of the forward reaction compare to that of the reverse reaction at time t4? Luckily, this is a good question. My students kind of choked on this one. Please don't choke again. So what we can see is that, look guys, as much as the concentrations are equal, because the concentration of the products at that point and the concentration of the reactants is actually equal, as in size or in amount. Okay, the amounts are equal, not necessarily constant, but exactly equal. But what is happening there? We will see that, no man, there's still a gradient here. There is still a gradient. So if there is still a gradient, we can see that, okay, we don't care about the steepness because these are two different graphs that are going in different directions. It's not really easy to comment on how steep one gradient is to the other because they are representing two separate, rather opposing phenomena. But all I can tell you guys is that if we have not reached this position where these are parallel, it means the products are being formed more than we are forming the reactants, isn't it? The forward reaction is still ongoing much faster than the reverse because the reverse is still catching up. So before equilibrium, always the forward reaction is going to be faster than the reverse. So that is the essence of this thing. If we have not reached equilibrium, the forward is always faster than the reverse. So we're going to say higher than. Okay, because the question is saying, how does the rate of the forward reaction compare to that of the reverse reaction? It's higher than. Because we have not yet reached equilibrium from start. So always the forward reaction is faster. Because if we look at the gradients of the two individual graphs, it's not going to be helpful. But one thing for sure is that logically, we are still forming products and we have not reached where the two rates are equal. So the first reaction is the forward reaction, and so it's going to be higher than the reverse. Yes. That's the one, guys. So easy 1 mark, okay, not so easy. It's easy to get confused there. Okay, 17.3. Okay, 17.3 says the equilibrium constant for the reaction is 0.04 at temperature T. Calculate the number of moles of iodide gas. Sorry, of iodine. Okay, I2. Okay. Present at time T6. And we can see at T6, this is when we have reached equilibrium. Right. Okay, so we're wanting the equilibrium number of moles of iodide gas. Right. Not a problem. We're told that we've got 2 moles of hydrogen iodide gas, essentially decomposing into hydrogen gas plus iodide gas. Okay. Right, the equation is balanced. So initially, what did we have in terms of number of moles? We were given the concentration. Right. That was at the beginning. So we know that concentration is going to be equal to number of moles. So this is 1 equal to number of moles divided by volume. Now this is going to be 0.5 actually. And we know that this is going to give us nothing but 0.5 moles when we cross multiply. But at the beginning, there shouldn't be anything of the products, okay? Change, number of moles. What was the change? We don't know. You can call it X, you know? Yeah, why not? But now, since this is going to be halves, we can just make it by 2 and say 2x so that we can avoid a situation where we have halves. Sometimes fractions, when they can be avoided, please avoid them. But if you can handle them, by all means. So at equilibrium, what is the story? So basically, guys, this is going to be nothing but 0.5 minus 2x. That's all. Then here we're going to have x because we are adding. Equilibrium concentration going to be 0.5 minus 2x divided by, what was that container's volume? 500 centimeter cubed. So this is just 0.5. So this will be x divided by 0.5, x divided by 0.5. Now that our table is complete, we can put it to work. Kc is going to be the concentration of iodide gas times, no, why am I squaring? It's not the case. So that of hydrogen, don't go. Ke eng ka wena jwale wa tla nseleka ntho towe ska nketsa jwalo hle ha ke batle o kwata hona tjena ke thabile hampe e seng hampe ke thabile haholo jwale ha ke batle he ntho e tla nketsang hore ke ska ikutlwa hantle wa bona ska nketsa fela ke ska ithata wa bona So essentially this is 0.5 minus 2x divided by 0.5. That is to be squared. Okay, let's work it out nicely. We've got 0.04 equals, if we simplify here, we get x over 0.5 all squared divided by 0.5 minus 2x divided by 0.5 all squared. Now we can see we've got square roots, so we can take the square root on the one side. Whatever we do on the one side, we must also do on the other. Yes. So let's do it. So square root of 0.04 gives us 1 over 5. That's literally 0.2. Okay, so basically what happens here, we just end up with x over 0.5. All of that divided by just 0.5 minus 2x over 0.5. Alright, okay, alright, so we divide this by 1 and then cross multiply. So this is just going to be some, mathematical gymnastics taking place here. Part of me feels like I could have handled things a bit better here. Because this situation here, let's clean it up here first. So we would get x over 0.5 times. We multiply by that flipped, just to make it a bit easier to handle. And we know that these guys will do the thing. And then we cross multiply thereafter. So I'm moving quick, guys. So this is going to be 0.5 times 0.2. So 0.5 times 0.2 is just going to be 0.1. Ne? Yeah, so this is going to be 0.1 minus just x is equal to x qwaba. Bona ke ngoku sekhona i-disaster. Re na le bothata. I don't think so. We don't have mathata. I'm just panicking. So this implies that 2x is equal to 0, 1. You can say therefore x is going to be 0, 1 divided by 2. Right? 0, 1 divided by 2 is 0, 0.05. But that's not the answer. Hayibo. Mangancikaza nisabona kahle sekumnyama la. Sekumnyama. So I don't even see what I'm adding. Hey. Tenses nengxaki ngoko. Because the range that we were given, let me see though, what is this thing? 0, 1 divided by 0. No, divided by 2. I'm getting 0, 0.05, but this one is smaller than the range that we were given. That's not nice. That's not nice. It means our simplification got botched. Oh, yeah, now what is this now? Yabona yena soxabana yena. Sesiyoxabana ke ngoku, sesiyaxabana. Yeah, there was a mistake here. Una lady mistake. Come on. Some serious mistakes now have occurred. But why is it not working, guys? But that answer cannot be accepted, eh? I'm thinking something is not right. Now this is not cool now, is it? Yeah, there's something I didn't do right. I think so. 0, 2 times 0, 5. But why is it 0, 5, man? Is it 0, 5? Yes. This thing is defeating me most now. Can't do it again to Lord of Lords, my mistake. Was 0, 2 times 2 is not 0, 1. Damn it, it's 0, 4. Damn it, man. Okay, the problem is here. So this is minus 0, 4x. Okay. So at the end, we're going to have 1, 4x. Right. Let's see now. 0, 1 divided by 1, 4. Okay, right. There it comes. So this is going to be 0, 0.07 to 2 decimal places. But again, we see there's 3 there. So that's it. moles. Okay, that's it, guys. X was the concentration of the hydrogen, sorry, of the iodide gas, and of course, X represents that. I ran out of space, so I am lazy to correct this. Okay, guys, let's see. We get a mark for the business, right? We get a mark for taking out the square root. It's a gymnastic. Writing out our Kc expression specific to this. Substitution, so 1, 2, 3, 4 marks. Yeah, and then 5, 6, 7. This is key. This is 8. And any of the changes, whether we say equilibrium or not, is not a problem here. 9 marks, guys, in the bag. In the bag. Right. So however this is marked, we're getting the marks. Now let's finish, guys. Let's finish. So 17.4 says the graph below shows how the rates of the forward and the reverse reactions change with time. Now the question is it for the graph that we have? We ended at equilibrium when these were equal. That was at 6 minutes. Can you see it starts at 6 minutes too? So this is likely that this is the same materials, right? Because they start off at equilibrium right there. And of course, a disturbance is introduced and they initially change together, but this reaction is favored more and it is indicated what the other one is. Okay. And of course, we've got the reverse reaction also considered. Now, this is a very good thing to look at because we would not be able to decide which one is which when we don't start from the beginning, okay? So this is why that key is given. But if it started from the beginning, it would not be necessary for labeling. In fact, it would be a question for the student to decide. Okay, 17.1 says the temperature of the container increased. Okay, so that's the disturbance. Again, we will see that there were two possibilities. It could be temperature or pressure, because pressure initially increases the concentrations and therefore the reaction rates will start to pick up sharply like that. But the one that's favored would then be more than the one that is playing catch up. But if we look at our equation, pressure would favor the reaction, of course increased pressure would favor the reaction with the least number of moles. But we can see there's 2 moles on the left, there's 2 moles on the right. So pressure would not affect the equilibrium position in this particular system. So it leaves temperature. I wish, or at least be aware that in the next question, if this question is repeated, you would probably be asked what was the disturbance and explain. Okay, all right, so we've got 17.4.1. Says which reaction or reactions shows an increase in the rate at time 10 minutes. Choose from forward, reverse, or both. Remember, at 10 minutes, not after 10 minutes. At 10 minutes. They both show an increase, so it's going to be both. Reverse reactions. Okay, both forward and reverse. That's what we were told to write. Okay, 17.4.2. Yeah, the dude is tired. Guys, it's not even funny. Now the question is the heat of the reaction delta H for this reaction positive or negative? Fully explain the answer. Okay. So as we can see, folks, we were not able to decide this because we didn't know the temperature. Okay. We didn't know. And now Kc, if we look at it, it's less than 1. So sometimes we can use the Kc to get an idea as to which reaction is favored by this particular temperature. But you can see Kc is less than 1. So it means this temperature T essentially favored the reverse reaction more than it did the forward, because we had less products compared to reactants. Now, we don't know though that temperature now, what it was, but we can see that with an increase in this temperature, we start to see that the forward reaction is favored, right? And if the forward reaction is favored by an increase in temperature, it means the forward reaction is endothermic. All right. At this point, Kc would only tell us that the equilibrium perhaps lay slightly to the left, but we couldn't be so sure which one is which because we didn't know what that temperature was. And even if we did know what that temperature was, we would not be able to make up our minds, I guess. But again, a decomposition reaction, guys, as we said at the beginning, it is likely to be an endothermic reaction. Okay, but some substances can decompose at room temperature, but mostly they would not. Okay, so this is easy. So we're going to use here our Le Chatelier's principle by looking at which reaction got favored by an increase in temperature. So this is the best one to look for. Okay, now it says, we said delta H here is going to be essentially positive. Delta H is positive. Can you see, guys? We get asked things that we discussed. So why is it positive now? We can say at T10 is at 10 minutes. The rate of both the forward and reverse reactions initially increased. Okay, the forward reaction is favored. Okay, and we can say an increase in temperature favors the endothermic reaction. So this is technically where Le Chatelier's principle comes in here. And we can say, therefore, the reverse reaction. No, not reverse. The forward, ne? Therefore, the forward. Oh, Nkosi yami ukubhala okunje. The forward reaction is endothermic. Therefore, delta H is positive. Okay. So we need to state things, guys. We need to state things and use principles. Again, precision, precision, precision. All right, so let's have a look here and see what is cooking. So again, folks, here it was a matter of choosing. So 1 mark. And saying positive, that's a mark. We can see that initially the 2 reactions increase, that's 1 mark. And then the forward reaction is favored. Okay, we can see that. But we know that according to Le Chatelier, that is what happens. And so we can state that the forward reaction is endothermic. That's good. And of course, delta H being positive, we've already gotten a mark for that. So in essence, we can say maybe that mark goes there. But we're supposed to get 4 marks now. I'm giving more. Okay. 1, 2, 3, 4. That's it. All right, guys, you can see that it's easy to go around these topics, but precision is key when handling questions in these topics. So a very vague understanding, a poor understanding here leads to disaster. As you could see, I also almost got my, I almost got my behind kicked by one of the questions by being emotional too soon without understanding. And I like it when this happens because, guys, I am trying my very best to actually demonstrate to you, how things work. And I like it because, you see, when one does these things on a fly, freestyling and all, you start to see a similar situation as you face when actually writing these exams, because you start to see how easy it is to make a mistake in understanding what is being given, because you already have a background knowledge of the practical background of this, that look, this diagram is crazy. But again, one didn't pay attention to time aspects like that precise moment. So this is very, 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 very important. So I hope you understand what is necessary now. And please, guys, there's plenty of questions. You see, lots and lots. This one was 2022, May, June. Very interesting. I've done it on the channel. So some questions I have done in the past. And of course, some I have discussed with my students. There's plenty, guys. Like, these are the ones we did. Lots of questions for students to actually look at. And they're quite interesting, by the way. So these are the ones that we did. So please, guys, do as much as you can. And make sure you understand. If not, please perhaps put your questions on the comment section if you're not someone who has access to our WhatsApp group. But those who have access to our WhatsApp group actually get better and quicker responses, because it's easier to just make a solution and screenshot and send it. But we can't do it on YouTube comment section, right? So those who really are part of the group are at an advantage, because they get comprehensive results for any of their questions that they may have, irrespective of the subject. Of course, between maths and physics at this stage. But I will slowly incorporate life sciences into this. But perhaps more of the parts that I can claim I have a bit of an expertise in, but other aspects may be quite a disaster. But again, I don't think there's a portion of biology that I don't understand fully. But it's just the way you guys get examined and how you are supposed to answer that frustrates me. As a result, I'll probably be giving you bad advice rather than good advice, because as good as the advice I would claim it is not quite acceptable at the moment by your standards of your exam guidelines and stuff. So for me, it's already going on in the way that I do not like a subject to be run. And yeah, I have seen even someone who understood this subject well enough, but not making it because of how they're supposed to answer. That's just ridiculous, man. Anyway, that's it. Let's not get into other subjects at the moment. Right, guys, so we're doing well with time. So now we are done with chemical equilibrium. Now let's hit acids and bases. But I just need a short break. Then we continue. Of course, we'll try to take this down under, should I say, 7 minutes. I mean, under 7 hours. That should be enough. All right, guys, so let's continue. So I've had some rest. I don't know, today I'm just a bit distracted, so I'm not feeling like, in the right mood to doing these videos. But hey, guys, for you, I will walk a mile and even take it further if I have to. Okay, acids and bases. We deal with properties, most grade 10 stuff or even grade 9 stuff. They taste sour, they turn blue litmus paper red. They increase the concentration of hydrogen ions in solution. I think that is the key for this topic in grade 12. And of course, to understand that they essentially decrease the concentration of hydroxide ions, and essentially we get low pH values. Right, bases, again, they taste bitter and never so beer. These turn a red litmus paper blue. Essentially, they neutralize our hydrogen ions in a solution. These increase the hydroxide ions in the solution, increasing the pH essentially. Right, of course, there's theories about what is an acid versus what is a base. So we need to know these two guys' theories, Lowry-Bronsted as well as the Arrhenius model. Okay, this is important definitions. Usually with this topic, there's not much of an explanation, but rather a definition and essentially an answer that may come from either, just theory or, from just some deduction of some sort. And then after that, it's going to be the big bad boys again, because girls are never big and they're never bad. Right. Let's see. Very important concept of conjugate acid-base pairs. This is one important issue that needs to be understood, guys. Please ensure that this is clear. So this pair differs from one another by a proton, okay, within an acid-base reaction. So that's what is important. Sometimes this can be asked as a question: how does an acid-base pair differ from one another? They differ by one hydrogen, or at least one proton. Hence we call these acid-base reactions protolytic reactions. It's protolysis reactions, so to speak, because we are transferring a proton as opposed to, by the way, what we call where electrons are transferred. Yeah, what do we call this again? Yeah, I forget, guys, but there's a term that describes the transfer of electrons. Here we are transferring we're transferring a proton, or a hydrogen plus ion. Okay, so of course, guys, this explains things. Again, please know about amphiprotic substances, or the so-called ampholytes. So these ones can behave as either an acid or a base depending on the reaction they're taking part in. Okay. So again, this is very important to know the conditions that in the presence of a strong acid, an amphiprotic substance will act as a base. And of course, in the presence of a strong base, this will act as an acid. Okay, right. Right, folks, so please read through these, of course, know the examples of strong acids, please, 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 and strong bases. Where are they? Yes. The metal hydroxides make up the strong bases, okay? Of the acids is HCl, H2SO4, and nitric acid. It seems like hydrobromic is mentioned there. It's not so commonly featured, so whatever sounds a bit different, I think it's worth remembering because it may cause problems if it shows up in the exams. But what we often know, it's easy. I mean, we know phosphoric acid, we know hydrofluoric acid, we know oxalic, we know ethanoic acid. But sometimes people may not realize that the hydrofluoric acid is a weak acid. It may be confusing. So these are things that you would want to, the unusual stuff is what needs to be, highlighted. The usual stuff, it's already well known. Okay. Right. So what do we mean when we say an acid is strong? It's because it dissociates completely in water, okay, as well as an acid. So again, this could be a theoretical based question or a question that needs an example, okay. So of course, folks, we need to do things, okay. Again, something to really remember is the auto-ionization of water at room temperature. It helps us a lot to determine a pH, especially for what is a base when it is not directly an acid. It helps us a lot. Okay, guys, very important is to know, the pH scale and to know exactly what we expect to be where, all right? And in essence, we need to know about indicators. This is usually the problem for many students because it's easy to forget. Because instead of using these in the lab so that we can know these for sure, it tends to not be the case in many schools. So it becomes a theoretical thing, which is essentially a practical thing. So now it becomes very difficult to remember this because it's either you know or you don't. This is something I emphasize in students to actually look at before entering into an exam. And of course, look at those pH ranges. It doesn't become so difficult. And in my opinion, because this is so easy to forget, I would also suggest that many of you who don't feel so confident in acids and bases, that you start with acids and bases. Do your best, get as many marks as you can, so that you can fly over the other sections because you have enough information to respond to questions in those sections. But this one, you cannot come to it tired when you're not strong in it. So whatever you're not strong at, please start with it so that you can give your best uninterrupted, not disappointed by your favorite section when it changes and becomes alcohol in your gut. It happens. You will say, I love organic chemistry, and then organic chemistry changes on you. Then you come here already beaten, worried, you will be sunk further. So you better start here, gather some confidence that, look, I fared so well. Then you go with enthusiasm and confidence in those other sections where you stand a very good chance to score some decent marks. Again, guys, a topic that is often overlooked by students, which is quite important, hydrolysis of salts. Please read this. Please read this and read it well, okay? So that is the basis to it. This is the basis to it. So very, 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 very important. A strong acid and a strong base will neutralize each other to give us the pH of water, okay? Because we produce water only. And salt. Even the salt is a neutral salt. Okay. Right. Again, here's an outline to show whether a salt is going to be acidic or basic and all that. There are some examples, guys. Please go through those. I'm not going to do that. Now we need to know issues about titrations again, okay? Again, we also need to understand how to dilute an acid. You don't pour water onto an acid, but you pour an acid onto water to do the dilution. If you pour water onto an acid, you will have a disaster. Okay, so we need to know how to dilute. We also need to know, when we're doing this, there are some terminologies that we need to understand. Okay, right. So yeah, we need to know about burettes and how to read sometimes information from a burette in answering questions. This is what usually gets students in trouble as well, because many never got the chance to do some practical work, so this becomes more of a theoretical thing, and yet it's supposed to be practical. Here are the most important tips on how to deal with questions that involve the stoichiometric calculations, which is the big bad boys in this section. Okay, so this helps a lot. Please read through this and understand issues at STP. Okay, when we've got some gaseous results in there. All right, here are some terms and definitions that, guys, you need to know. Right, please, you need to know what is an indicator. You may be asked a silly question as to what is an indicator, and at times what is an acid indicator or whatever. Yeah, let's just say an indicator, And what is an ampholyte or an amphiprotic substance? We need to know this. The models, Arrhenius versus Lowry-Bronsted. What else? Yeah, there's a lot of things, guys, that we need to know, especially things like what is dissociation. What do we mean when we talk of an endpoint? How does it differ from what we call an equivalence point? These are usually the problems. Again, as I said, folks, precision with these topics is what is important. Otherwise, a very loose understanding will land you in hot water. Okay, so that's it. Sometimes you may be asked, what is a standard solution? So it's mainly definitions and terminologies here. All right, so you may be asked about a titration. Sometimes maybe given a scenario that signifies a titration, and then you'd be called, what is the term referred to what is happening? And again, what is a weak acid? What is a weak base? What is a strong acid and a strong base? These are typical questions that one needs to be ready to respond to. All right, grade 12s. Yeah, let's see what questions we can choose for this last part of our revision. All right, guys, so let's look at some questions and start moving. Okay, maybe we can do 4 questions, so that we can just get you into the groove, guys. All right, what I like here, there's not a lot to explain, but more to just give. Right. 1.1 says, nitric acid, an important acid used in industry, is a strong acid. Give a reason why nitric acid is classified as a strong acid. Can you see? Very easy stuff. So we've got 1.1.1 because it dissociates completely inward to give a high concentration of hydrogen plus ions in the solution. Okay, let's leave it at that. Right, the issue here is the complete dissociation in water. That's why. Okay, so we've got 1.1.2 says write down the name or formula of the conjugate base of nitric acid. What did we say? An acid-base pair will essentially differ by essentially one hydrogen plus ion, or by a proton. So we just take a proton away, we get the nitrate ion. So this is NO3 minus ion. Sometimes if we're told to give a name, we give a name or a formula, but not both. So this is the nitrate ion. Okay? Please know how to name these things, or at least be able to see how to do this. Okay, again, easy 1 mark. So 1.1.3 says, calculate the pH of a 0.3 mole per decimeter cubed nitric acid solution. So this is easy, guys, because we know that the nitric acid here, HNO3, aqueous, dissociates in water. I don't know what I'm writing there. To form the oxonium ion plus the nitrate ion. Okay. Right, so we can see that 1 mole of nitric acid produces 1 mole of the hydrogen ions. So due to the dative covalent bond, they end up being attached to the water molecule so that they're not free. Okay, that's why we form that oxonium ion. So in essence, if the concentration of the nitric acid, a molar concentration is given, we already see that the molar concentration of the oxonium ion would be the same, because the volume in which these are is also the same. So we can say essentially 1 mole of HNO3 produces or yields 1 mole of the oxonium ion. So this implies that the concentration of the oxonium ion is going to be equal to the concentration of the nitric acid. I don't know why I'm writing things. Hey guys, I think I'm distracted, seriously, I'm not at my best at the moment. So it's going to be the concentration that we are given, 0.3 mole per decimeter cubed. Please guys, go through these steps. Don't cut the corners. It's important. Then we know that pH is minus the log of the concentration of the oxonium ions minus the log of 0.3. Therefore, the pH is minus log minus the log of 0.3. So we get to 2 decimal places, 0.52. We can see this is a very low pH, typical of strong acids. It's way less than 7. This is highly concentrated for sure. All right, okay, not a bad calculation here. The main thing, folks, is formula, substitutions, answer. But substitutions here may not necessarily be so strong, but to be convinced that the concentration of our hydronium or oxonium ions or hydrogen ions is the same as that of the acid itself, because it's a strong acid. So that is the one. Okay, let's get to 1.2. (1.2) reads, A laboratory technician wants to determine the percentage purity, see we spoke about this, of magnesium oxide. He dissolves a 4,5 grams sample of the magnesium oxide in 100 centimeter cubed hydrochloric acid of concentration 2 mole per decimeter cubed. That's quite high. Calculate the number of moles of hydrochloric acid added to the magnesium oxide. Okay, how much did we have? 100 centimeter cubed of a 2 mole per decimeter cubed concentration. So we know that 1.2.1 concentration is number of moles over volume. So we're given the concentration here, that it's 2. We want the number of moles. The volume is 100 centimeter cubed, so when you divide by 8,000, we get a 0,1. Yes. 100 divided by 8,000, yes, is 0,1. So essentially, we can see that the number of moles is going to be 0,2. 0,2 moles. Right. Is it moles or mole? You're not lay. Right. Formula, substitution, answer, guys. Not a complicated question there. So 1.2.2. So the question says, he then uses the apparatus alongside to titrate excess hydrochloric acid, meaning the hydrochloric acid will be in excess after that reaction, okay, in the above solution against a solution of sodium hydroxide. So a strong acid, strong base. Now it says write down the name of the apparatus Q in the diagram. Can you see? That's a burette. That's a burette. So it helps to know, guys. Please know this is a burette, Allen-Meyer flask, a stand, call it a retort stand, and all. We need to know. This is a burette. Burette ubhalwa kanjani kanini? Is it like this? Khona lapho. Please double check. Double check, but it's a burette. That's what we call it. See, easy 1 marks. 1.2.3. All right, so we are told that the following indicators are available for the titration. This titration of neutralization of the excess hydrochloric acid. So we know this is a strong base reacting with a strong acid. So the resulting pH, when they neutralize each other, should be around 7. Now we are told that there's indicator A with a pH range of 3 to 4. That's less than 7, so that's an acidic pH. This one from 6 to 7,6. Can you see more or less around pH of 7? See, it's a basic one, so more like phenolphthalein and stuff. So no, so it cannot be this, it cannot be that, but this one would be the best choice if ever we get asked. Which one of the following above indicators, A, B, or C, is the most suitable to indicate the exact end point in the titration? Give a reason. Of course, it's going to be B. You can say it has a pH range for a neutral substance. That is pH of 7 and slightly around it. So it's not really that difficult, but precision, folks, precision is key. Right, so you see, it's easy to race through this exam. 1.2.4. So it says, goodness, 3 marks. Are you kidding me? Are you kidding me? Yeah, well, whatever, guys. I would say perhaps 2 marks for the explanation, or maybe 2 marks for the choice. I'm not sure. Either one of the two. It's either we take 2 marks or 1, and we take 2 marks or 1 for the explanation. It doesn't have to be complicated after all. But perhaps one can push it and say the titration is between a strong acid and a strong base, and so the resulting pH will be neutral. But again, what we're talking about is already suggesting that. Okay, let's see. During this titration, the technician uses distilled water to wash any sodium hydroxide spilled, okay, against the sides of the Erlenmeyer flask into the solution, okay. Now give a reason why the addition of distilled water to the Erlenmeyer flask will not influence the result. Very interesting. What is this question asking? During the titration, the technician uses distilled water to wash any sodium hydroxide spilled against the sides of the Erlenmeyer flask into the solution. Give a reason why the addition of distilled water to the Erlenmeyer flask will not influence the result. Of course, what is reacting is not the water, but the base itself. So its concentration, or should we say the number of moles of the acid, because it's not necessarily the concentration that we care about. We care about the number of moles. So even if we can dilute this and be so dilute that, you know what, you won't even feel the bitter taste, the reality is the number of moles of sodium hydroxide present is still the same. So yeah, I guess you can just say it's because the number of moles. See, this tablet likes to mess with me, man. Stop this thing, okay? We can say the number of moles of sodium hydroxide is not affected by dilution. This may only slow down the reaction rate, but the end result will be the same. Okay, but it's not affected by the dilution. And so the end result will be the same. Although, can just show that although it may be slower, right? Because you understand that if we decrease the concentration of one of the reactants, then the reaction rate is going to drop. Can you see, guys? To master these two beasts, which we can call one the leopard and one the lion, or a tiger. Remember, in Africa, we don't talk about a tiger per se. We're talking about a lion and a leopard. We don't talk about a tiger because in Africa we don't have such. Of course now we probably do, because people keep moving these things around and, you know, for whatever reasons promotes them to kind of keep this everywhere they want, but they don't originate here. Okay, so that's why we don't really have a name for a tiger. But of course, now that we know it exists, ibizwa ngengonyama nayo, but agyongonyama. Ingwe, ibizwa ngengwe. But now kuhambe kubuza imibuzo but i-tiger yona intoni, ngoba i-tiger is here in Africa. Well, i-tiger ngesixhosa sithi lihlosi, okay? Lihlosi, not ingwe. Ingwe, it's a leopard. Then the what do you call this thing? A cheetah. What did I say? I wanted to talk about a cheetah, man, not a goodness, I don't know. I just said kanti wenzeka ntoni kum namhlanje, yamadod. I'm just not doing well, eh? I'm not sick actually, but I don't know why. I'm just off. Right. Ingwe. Ne? It's a leopard. We don't have a name historically in Africa for a tiger. Okay, just a moment, guys. Okay, guys, so yeah, you just want to portray that this thing, you know, the integration of the topics, but you can see that the reaction rate is not the most important thing for this experiment, but more of the neutralization per se. So in essence, yeah, you show this. Of course, I was just explaining the difference between ingwe and ngonyam. Ngonyam is a lion, ingwe it's a leopard, then a cheetah, because it's African, that's what I wanted to say. Because I will call it ihlosi. Okay? Finish and klar. Yes, klar didings. Okay, let's do this one. Right. See, easy marks, guys. Easy marks. You can score these nicely while still fresh before you freak out. Okay, at the end point of the titration, he finds that 21 centimeter cubed of a 0.2 mole per decimeter cube sodium hydroxide solution has neutralized the excess hydrochloric acid. Can you see? Now calculate the number of moles of acid that was in excess. Okay, this is easy because we did calculate the number of moles of essentially the acid. Was it the acid? Yeah, we did. Now this acid, we can calculate the number of moles that were used up in this reaction. And from then on, we can work out our business nicely, okay? But the issue is that we were not given, an equation of this reaction. Can you see? That's just the catch. That's just the catch. We're not given the equation. And that is what can hurt if students are not careful. But again, this one is easy. We know that HCl plus NaOH is going to give us NaCl plus H2O. Right, so this is aqueous. That could be a gas if it is water vapor, but of course in the test tube is going to condense into water and fall back into the solution, so we can safely say liquid. So again, the key thing with this calculation was to know this. If this is not known, it's going to be very dangerous. As we can see here, 1 mole of base reacts with 1 mole of acid, right? So we can easily say that and say 1 mole of HCl reacts with 1 mole of NaOH. So this implies that the number of moles of HCl used, or we can say reacted, is going to be equal to the number of moles of NaOH used, or that reacted. So we go on and say number of moles of HCl is number of moles here. When we've got the concentration, is going to be concentration times the volume. This concentration was 0.2 times the volume we were told is 21 centimeter cubed. So this is going to be 0.21. Okay, and let's just check it on the calculator. So 21 divided by 1000 is like this, 0.021. So we know that we can make a conclusion that the number of moles of our HCl that we used is the answer thereof. So 0,2 to 0,021. So this gives us a 4,2 times 10 to the minus 3 moles. Okay. Now, is it moles or mole? I think sometimes it's written as a mole. Mole. We can say then the number of moles in excess but that's the one, isn't it? Yeah, man, that's the one. Therefore, the number of moles of HCl in excess was essentially this answer there, because this was what was left over and was essentially swallowed up by the base. Easy stuff, okay? Right. We've got it nicely, guys. It's easy, 3 marks. Otherwise, formula, substitution, answer. Of course, the substitution is more of the conversion of that. Easy. As you can see, guys, not a big deal, but key was to know the formula that is going to be a 1-to-1 ratio. Otherwise, it would hurt like... Ooh, I don't want to say. Okay, now the balanced equation for the reaction between hydrochloric acid and magnesium oxide. See, we're going back to the issues of number 1. Is this, okay, this is given. Calculate the percentage purity of the magnesium oxide. Remember, we were told that the magnesium oxide, we wanted to determine the percentage purity. So we understand very well that the percentage purity is going to be technically the amount of magnesium oxide that actually reacted, and then the reaction stopped because there was no more magnesium oxide. We assume that the acid can only react with the magnesium oxide. All right, so now we assume that, yeah, can you imagine, man? You just think about something and it's there, even if it's not there though. Okay, we assume that only the magnesium oxide in that 4,5 gram sample reacted with the acid. Okay, so let's deal with this issue. Now, folks, we know the number of moles in excess, and we know the total number of moles that we calculated in 1.2.1. So in essence, the difference is what will have reacted with the magnesium oxide. Okay, let's write the equation. MgO solid plus 2HCl. AQ gives us MgCl2. Right, plus the water. Great stuff. Now, we will safely say, okay, all right, okay. We want to know the percentage purity of our magnesium oxide. So we understand that, of course, guys, 1 mole of MgO reacted or reacts with 2 moles of HCl. Now we know enough, so this implies that the number of moles of MgO is going to be half the number of moles of HCl. Okay, so this implies that the number of moles of MgO is going to be half. Now, what is the number of moles of HCl that we used? It's going to be the difference between the total, which was 0,2, minus what was in excess, 4,2 times 10 to the minus 3. So we can find out that the number of moles of MgO is what we will get. Right, so we have a 0,2 there minus 4,2 times 10 to the minus 3. So this gives us, I'm just going to write it as it comes out, 0,1958 mole. Easy stuff. But now we can see that what we were given, the sample was given in mass. And so we need to convert this to a mass. Okay, just a moment. Alright guys, so my students are already needing me to go and begin the lessons with them. So unfortunately, I wanted to do more examples. I'm probably going to end up with just 2, okay? Let's try to push for 2 at least. Right, so this is what we have, folks, and we need to then convert this. We can say therefore the mass of MgO is going to be the number of moles times the molar mass. Magnesium is 20, is it 24? Which one is 24? Is it calcium? I don't remember. Anyway, I don't have to remember. I have a periodic table here. Kovela magnesium sun 24 nyan. Teni ndizithandabuzile. Alright, 24 plus 16. Right. So this is going to give us the mass in grams. 0,1958 times 24 plus 16. So this gives us a 7. Wait. I am not happy with this calculation. There's no way we can get a bigger answer here. Ah, goodness, I forgot to. I forgot to have this thing. Lord have mercy on me. I did not have it. Damn it, man. I was surprised. 0,2 into, no. 0,5 into 0,2 minus 4,2 times 10 to the exponent minus 3 is a different one. But it's the same thing, man. Then why am I getting things wrong? Damn it, man. Oh yeah, it's different. So this is 0,0979. Okay, so that's fine. So this is 0,0979. Okay, multiply this by I don't want to think. Now this one is talking to me. 3,916 grams. We can say then the percentage purity of magnesium oxide is going to be equal to the mass over the molar mass, right, multiplied by mass impure. Maybe let's say mass pure so that this is clear, divided by mass impure times 100%. So we know that this is 3,916 divided by that mass that we were given. What was it? 4,5 times 100. So let's get it over and done with. Divided by 4,5 times 100. So we're getting 87,02%. Okay. So these questions, guys, are quite popular, so we need to get it done, okay? We need to get it done. So that is it. You can see it's not quite a big question as students often think, but it can be quite challenging in that it demands a little bit from a student. Okay, let's see, guys. I'm distracted heavily. I don't know if I'm going to perform well. I've got a class and I've got a colleague who needs assistance. I don't know what's going to happen. But sobona khona, sizobona khona. Wakuthola khona, laba baby bayakhala, bathi weshebeleza. Sizokuthola khona. Ebumnandili, kula zokuthola khona. Ebumnandili, kula zokuthola khona. Wakuthola khona, laba baby bayakhala, bathi weshebeleza. Andinguye ushebeleza nijonge kahle. Dokushebeleza zizikhokho zekwaito ke lonto. Hayi le nonsense esiyimamelayo leculwa ngabantwana nabafana. That was the things, boy. There was a beat, the vibes. Right now it's noise and ridiculousness. Anyway, whatever. Guys, here's the thing. Here is the thing. Knowing how to calculate this number of moles is very important. But again, this is differentials is very important also. To calculate this number of dondons is also key. And we cannot exhaust the marks, right? Technically, the mass was key. Then we need to forfeit 1 mark here. This hurts. Of course, this is not so bad. We can forgive ourselves for that and say, yeah, this formula is key also, and the answer. Again, guys, the marks can be, put however one sees. That is that. So, folks, yeah, that is it. So I wish for us, guys, to have a look at this question. Of course, I wanted to do more, but now my students are calling for me and our time is an issue. So let me try to do this question and see if I cannot squash it, in no time at all. Because I would have liked to do more questions. You see, this thing of relaxing now backfired because I should have finished this thing long ago. Right. Anhydrous oxalic acid has what is an example of an acid that can donate 2 protons and thus ionizes in 2 steps as represented by the equation below. Right. And what do we call oxalic acid? The scientific name is dioic acid, isn't it? Right. Okay. All right. So we see all of that. Now, let's deal with the issues. I think we don't have the time to talk now. Now we need to write down one word for the underlined phrase in the above sentence. It's diprotic. Okay. 3.1.2. Score a mark there and smile on. The formula of each of the 2 bases in reaction 2. Right, the base here is going to be the water, H2O, and the second one is the dioate ion. So this is going to be the COO 2 with the 2 minus there, because we were told exactly in which reaction we are looking at this. Okay. Again, we were told to write a formula, so that's it. Easy 2 marks there. So 3.1.3 says the formula of the substance that acts as an ampholyte. All right. Okay, guys, just a moment. All right, so let's finish up, guys. We've got some work to do here. The formula of a substance that acts as an ampholyte in reactions 1 and 2. Give a reason for the answer. Okay. Now we can look at reaction 1. What do we see? This is an acid. It's a base. because it differs to the acid by 1 proton. So it's a conjugate base acid. So it's a conjugate base of acid dioic acid, or the oxalic acid. And then when we look at this guy again, we see that, oh my god, this guy is now all of a sudden an acid, because now it's protonizing water instead. Okay, so at that point it is an acid. So this means that is the one. That is the one. So we're supposed to write the formula. So it's basically HCOO to 1 minus as it is given to us there. Right. So that's the ampholyte, because in reaction 1 it acts as an acid. Wait, in reaction 1 it acts as a base, and in reaction 2 it acts as an acid. And of course we're supposed to give a reason for the answer, and that's exactly the reason. It is a base in reaction 1 while it acts as an acid in 2. That's why. Great stuff. Again, easy 1 mark. See, describe what you see. No issues here. 3.2 says, give a reason why oxalic acid is a weak acid. Can you see, guys, definitions? It dissociates incompletely in water to form a low concentration of hydrogen plus ions. Nice. Easy stuff. Again, it dissociates incompletely. That's the main anchor here. All right. Okay. All right. So we've got 3.3. 3.3 says a standard solution of dioic acid or oxalic acid of a concentration of 0.2 moles per decimeter cubed is prepared by dissolving a certain amount of this dioic acid in a 250 centimeter cubed volumetric flask. By the way, the word anhydrous, it means it's powder, right? Or it doesn't have water. It's unwatery. Anyway, calculate the mass of the oxalic acid needed to prepare the standard solution. Easy, guys. We know that concentration can be given by a mass over the volume times the molar mass. Okay. So the concentration is 0.20 equals, mass is what we want. The volume is 250, so this is going to be 0.25 into the molar mass of this thing here. So we've got 12 for carbon. We've got 16 times 2. Wait. Yeah, we've got 16 plus 16. Okay, maybe let me say times 2. It's fine. Plus, is there anything else? The hydrogen. Yeah, doch. There is a hydrogen, which is 1. And then we multiply that whole thing by 2, isn't it? Yes. 12 plus 16 plus 16 plus 1 times 2. Yes. Subscripts count here. They count. So maybe let's move this guy so that it's not sitting on the edge. It's like it's afraid of the business here. So the mass here is going to be 0.20 times 0.25 times. Let's calculate that value there so that it doesn't give us headaches. 12 plus 16 times 2 plus 1. That's 45 by 2. It gives us 90. All right, so let's see what is that mass now. We then multiply this by 0.2. Gives us 18 grams. You are kidding me. The answer there is 4.5 grams. Am I being punked or something? I cannot be punked, guys. No, 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 no. Maybe my concentration wasn't right. Let me see. Oh yeah, oh yeah, oh yeah, oh yeah, oh yeah. I forgot the 0.25 here. I was surprised. Why am I being punked? It's not nice to be punked. I'm a Nancy Angela. It's no fun again. We're not gonna be friends. It's dribbling me now. And guys, I don't have time for this. I don't have time for this, you see. Let's start again. 0.20 times 0.25 times 90. Huh? Okay. Is 4.5. So I did a dangerous maneuver here. I was surprised, but hey, you got to check, guys. As you can see, if you come to these sections tired, even I make some lousy mistakes. You can imagine when you come here under pressure to score marks and you fail to get this done. So it becomes a horrible situation. Okay, guys, I'm racing against time right now. Formula, this calculation, general substitutions, answer. Nice 4 marks there. Okay, let's get to the big question here. So we've got 3.4. Maybe let's just start it on a new page straight up. So I need to move now, guys. 3.4 says, during a titration of the standard solution of the dioic acid prepared in question 3.3 is neutralized by sodium hydroxide solution from a burette. The balanced equation for the reaction is what we have been given. Now, the diagrams below show the burette readings before the titration commenced and at the end point, respectively. So we can clearly see there that we are looking at 3 right now. Okay, it's sitting at 3 over here. Okay, all right. That was before the titration. And we can see this 3 is centimeter cubed. And when we look at it again, the level here at the end point is sitting at, just above 39. Okay. Now I'm trying to find out what on the Lord's earth is going on here. This is crazy. The level was 3, and now this is 39. Highway. Funuktin. What are you trying to tell? What are you trying to tell? I God. Oh, question, come on, man. I don't have time for this nonsense, I'm trying to think, guys, what is going on here? What is going on? Is that supposed to be 3? Yikes. This question is dangerous, is it not? Yeah. It's dangerous. Okay, all right, okay. Now this is percussing me. And my worry is that time, guys, is against me 100%. Yay wena, yay wena, yay wena, yay wena. Why do we have 38, 39? And then we've got 3 there. Hayi. Ha bandla sekuyabheda kakhulu ke masekunje. Angisazi. Okay guys, so this is problematic. I can't solve this thing. I thought I was gonna do it. And now it's doing me things that I don't like. Oh, Nkosi yami abafundi bam. Let me warn them that I need 5 more minutes. Maybe 10 more. Otherwise, bazokwata. Because I need to think about it now. Okay. Right, so let's see, folks. What are we supposed to do now? I can't read this thing. This burette is giving me goosebumps now. I remember a question like this I've done before, but in so many ways now it's not making sense the way it looks. But I'm looking at this meniscus. You see the meniscus is upturned. Usually this is the top end of the thing, it's the top end usually, like that, So for me, it gives me the impression that at the very top, this burette has 1, 2 going down. At the very bottom, it has the highest value. And we can see that now this has come down from that. So once the meniscus is upturned, it means that is the top side. Okay? So again, it takes a bit of a moment sometimes to figure out what's going on. So be familiar with these kinds of things. Again, experiments in class help as well to get this done. Of course, guys, this is going to be our last question, as much as I would have liked to do one more. Okay, so we can see what is cooking here. So basically, guys, as we can see from 3 here at the top, we moved all the way down to basically, 30 what? 1, 2, 3, 4. So this is 2, 4, 6, 8. So that's 38. And of course, if this is 2, 2, 2, 4, 6, 8. So this is 2, 8, not 28. Okay. All right. Okay. So how much have we given? This is crazy, man. This is crazy. How much have we given now? That's the good question. At least we established the levels. But now we need to know how much of this solution of the base have we given, because it matters. Okay, let's think about it. Okay, to solve these problems, folks, we need a strategy. So let's just think of ourselves having our own burette right now. And say this burette of ours, we just tried to create one like this and say this was 1, say 2, 3, 4, and 5. So let's say this is 1, 2, 3, 4, 5. Now let's say our thingy was seated here, and then all of a sudden we are seated here. So this means this is what we gave, right? The difference is what we gave. So as we can see, if we say 5 minus 1, it gives us exactly how much we got, because we got 1, 2, 3. 4. Okay, we gave 4 meals here. Right, so it's 1, 2, 3, 4. Yes, we gave 4. So the same thing, we're just going to take this one and subtract the first one. And that's exactly how we're going to do this. We're just going to say 38. This is 38,8, not just 38. Okay. So we're going to say 38,8 minus 2,8. That gives us exactly how much we gave. So that was a tricky question. Okay, so 38,8 minus 2,8. So it gives us 36 centimeter cubed. Okay, nice. So you see, with these kinds of questions, it can hurt, of course, if precision is not the case. So you can see, guys, you cannot walk through these questions under pressure. So start with these silly boys and deal with them. And then you can go and enjoy your time elsewhere. You can go there in a hurry, but not here. Precision is key here. So we've got 3,4,1. Okay, I like this question because it forces one to think of a model. And that model answers the question nicely. All right, so let's get to the business. It says use the burette readings and calculate the concentration of the sodium hydroxide solution. Okay, we are looking for the concentration of the sodium hydroxide solution. Of course, we know more about the acid. We know just we only know the number of what? We just know the volume of the base, but we don't know the concentration, and that's what we want. Okay, again, guys, what did we reach here again? During a titration, okay, the balanced equation, the diagrams, okay, we've reached the end point. So, of course, this means there's nothing left over here. I hope so. But again, here we have the luxury of seeing the marks, but at the same time, to see the answer, but under normal circumstances, it doesn't come out like that. So if nothing is left over, we can use this one. Concentration of acid times volume of acid over concentration of base times volume of base is going to be equal to the number of moles of the acid over number of moles of base. But remember, we only use this when this is a complete titration or complete neutralization and nothing is left over. Okay, what's the concentration of the acid? We calculated it above, didn't we? In fact, we were given that it's 0,2. So this is 0,20. The volume, we were told that it's 25 centimeter cubed. So this is 0,025, all divided by. Now, the concentration of the base is what we want. The volume of the base is 0,036, right? Saying that this is what we needed. Very interesting stuff. Okay, equals, and then from the equation, we know that 1 mole of the acid reacts with 2 moles of the base. So this is 1 over 2. Okay, we can say simply the concentration of base. Okay guys, I'm under pressure right now. Is going to be essentially 2 times 0,20 times 0,025. Of course, here I did not even need to convert these actually. I shouldn't have, because these ones take care of each other actually. Let's not waste time here. Let us not waste time. So we don't need to convert when the units are the same. So this was 25. This came out to be 36. So this is basically 2 into 0,20 into 25. And then we'll divide this by 36. Right. Therefore, the concentration of base is... Okay, this one was a very easy question, it seems, unless I botched it. If I did... ningasangiburara, angifuni kufa mina. Siyibethile bantram. Ibethwe yayoxela. This is 0.28 mos, yeah, to 2 decimal places. This is mole per decimeter cubed. Sinqobile noba ithande ukusiphekasa kancinci. Okay guys, I wish I could do more, but again, you can see that reaction rates do apply everywhere where we see a reaction. And folks, you should be on the alert that things must be done properly for a proper result. Okay, so let's finish up here. Easy 5 marks otherwise. So we get a mark for the formula, we get a mark for getting this dude. General substitutions, and of course we can even say general substitutions on the left and that molar ratio, and essentially the final answer, just to make up the 5 marks. Again, someone else may have approached it in a different way, but it's not a big deal for now. So let's look at 3.4.2. This one says, write down a balanced equation that explains why the pH of the solution is greater than 7 at the end point. This is talking about hydrolysis of salt. Hydrolysis of salts. Now, we know that we reacted a strong base and a weak acid. So the salt that results is a basic salt. So this one will actually be hydrolyzed by water. So let's show that. So we know that, okay, the COO, basically 2 minus. Is it 2 minus? Yes, we lost 2 hydrogens. So we can say 2 minus. Right, plus water will give us, or will give it us. Remember, water will act like a big boy this time. It's going to say, okay, in the absence of the strong ones, I am the strongest. So it will protolyze, but you don't show what I'm doing right now. So what happens is we get HCOO minus plus the production of the hydroxide ions is the friend. This is the one that's responsible. It's a strong base, that one. So it's responsible for this. Again, please guys, master your craft. Master your craft. You will go far. You don't, you're not getting anywhere. So I suppose the left hand side here, this dude is key, and the overall thing, extra mark for your troubles. All right guys, we cannot go further than this, unfortunately, because of time and my commitments to my students. So I have to leave and love you. I wanted us to look at this question as well, question 4, as well as question 7. So you can try those questions and every other question, of course. I'll probably do a separate video to handle those 2 questions once I am done with what I need to do now. So let's see each other in the next video. And of course, there's plenty of questions, guys, to dance with. And this paper is complete. You see, it goes into electrochemistry and giving all the ideas about them, questions. You do as many as you can. And of course, I do hope that you will do well. Otherwise, I will meet you, those who are my students, when we do revision for the finals. We're going to discuss all of these little documents that I've given to you guys. And of course, we'll take some of the trial papers that are going to be written here and discuss them during the classes. Well, yeah, for others, folks, please watch the channel. For some of the trial papers, I may do some, but not all. At the very least, I'll do one for paper 2, perhaps one for paper 1, one for paper 1 maths, one for paper 1. No, one for paper 2 maths. It will depend, of course, on the time I have on my hands. And of course, I can do more, but I will not promise to do more than just those 4 papers for the trials of this year. But for my students, we're going to review as many trial papers as we find. Of course, we're going to pick the nice questions. Otherwise, there's no point in us doing the entire papers. Some questions are fairly easy, so we'll challenge ourselves with those nice and technical questions. All right, guys, I hope you will have learned something out of this video. If not, too bad, but if yes, well, all good. Please leave a comment, show a support with a like. You can consider subscribing because there will be things coming. And the reality here is that I do not have that much of a consistency in doing so. So as a result, there is some inconsistent posting because of my very busy time schedules. As you can see, I'm pressed 100% even right now. So it helps to subscribe because you'll never miss an upload. And of course, do hit the notification bell so that you don't really miss it at all. You will even hear the notification letting you know beforehand, because some videos I schedule so that you get to see them well before time. All right, guys. Otherwise, good luck with your trial exams. We'll meet when we are heavily preparing for the final exams, which I hope it's going to be a smooth sail. Otherwise, all the best and goodbye.